The first thing the camera sees is not an animal, but a number. It glows on a monitor in the control room while the vehicle drops beneath the ship, a white depth reading changing too slowly for anyone to stare at for long and too steadily for anyone to ignore. 200 meters. 400. 800. Outside the ROV, the last usable daylight has thinned into a blue that looks almost artificial, and the steel frame around the cameras has already entered a world that would treat an empty can like paper. The machine is not being pushed from one side. It is being pressed from every side at once. Every seam, every screw, every lens, every hollow space is receiving the same instruction from the ocean. Become smaller, or fail. This is the first rule of the deep sea, and it is not darkness. Darkness arrives early, but pressure never stops arriving. It increases with depth as the weight of water accumulates overhead, not like a falling object, not like a storm, but like an invisible geology made of liquid. At 10 meters, the pressure has already doubled compared with the surface. At 1,000 meters, it is roughly 100 times greater. At the bottom of the deepest trenches, the pressure is more than 1,000 atmospheres, and it is so constant that it becomes part of the place, as ordinary there as wind is ordinary on land. The strange part is that the water itself does not look heavy. A camera beam moves through it, as though through clear air filled with drifting specks. A jelly turns once, slowly, and disappears behind the machine. A small fish holds position above a ledge without seeming to struggle. A brittle star folds itself over a piece of sinking flesh. Nothing in the frame is shouting that a pressure exists strong enough to crush metal housings, distort glass, and collapse human lungs. The pressure is not visible because it is everywhere. It has no edge, no direction, no dramatic front. It is the background condition that all of these animals have always known. If these quiet descents into the hidden ocean are what bring you here, subscribing keeps the next journey close. The title of this world could sound like a warning written for engineers, because it often is. Pressure worlds are where material strength stops being a simple idea. A flat plate can bend inward. A badly shaped chamber can buckle. A hollow instrument with trapped air inside can implode so quickly that the failure becomes its own small explosion. The ocean does not need teeth to destroy a machine. It only needs depth. And yet the same depth that can fold metal also holds animals with transparent bodies, soft fins, delicate antennae, gelatinous bells, and eggs small enough to vanish into plankton. The contradiction is not that the animals are strong like machines. The contradiction is that machines are built with emptiness inside, and most deep sea life is not. A human vehicle must carry a surface world downward. It must bring air, electronics, batteries, camera cavities, connectors, motors, and sometimes people. These things require compartments, and compartments require walls. The deeper the vehicle descends, the more those walls become the boundary between two incompatible conditions. Inside is one atmosphere, the pressure our bodies evolved to tolerate. Outside may be hundreds or more than 1,000. The difference is what breaks things. A deep sea animal is not carrying a room full of air through the water. Its tissues are mostly water, and water is difficult to compress. Its body is not a pressure vessel in the engineering sense. It is part of the pressure world, not an intruder trying to resist it. This does not mean pressure is harmless to life. Proteins can change shape under pressure. Cell membranes can become less flexible. Chemical reactions can slow or shift. Gas-filled spaces become dangerous if they are not controlled. Animals that live deep are not simply shallow animals placed farther down. Their bodies are tuned, sometimes in ways that are still being studied, to keep cells working under forces that would damage or stop the same processes in their shallow water relatives. The adaptation is intimate. It happens at the level of membranes and enzymes, in the chemistry of muscle and nerve, in the way a fish builds or avoids a swim bladder, in the way a gelatinous animal keeps its tissues from becoming too rigid or too fragile. To understand these pressure worlds, it helps not to start at the bottom. Start at the surface, on a calm day, where the research ship rises and falls in ordinary swells. The ocean looks open and breathable there. Gulls may follow the wake. Sunlight flashes on the winch cable. People in hard hats stand near the stern, while a yellow vehicle hangs above the water, its lights dark, its manipulators folded inward, its frame dripping from a test dip. The ship is part of the air world. The machine below it is about to leave that world behind, but it cannot stop belonging to it. That is why it needs armor. Engineers protect deep-sea instruments with shapes that distribute pressure cleanly. Spheres are favored because the force presses evenly toward the center. Cylinders are used when they can be made strong enough, and when their ends are properly designed. Corners are problems because stress gathers there. Large flat surfaces are problems because they invite bending. A small imperfection can matter. A scratch, a bad weld, a weak seal, a tiny void in the wrong place can become a point where the ocean begins to enter. At shallow depths, the mistake may be survivable. Far below, the mistake may have no gradual stage at all. This is why a submersible looks less like a boat than like a set of decisions about pressure. The human space may be a nearly perfect sphere made of titanium or steel. The batteries may be kept in pressure-balanced oil. The flotation may be syntactic foam, not ordinary foam, but a material filled with microscopic hollow spheres designed to resist compression while still providing lift. The lights may sit behind thick windows. Cables must pass through penetrators that can survive the difference between the electrical world inside and the ocean outside. Every part of the vehicle is an answer to a question the deep sea asks continuously. What inside you is hollow? And how long can it remain that way? Then, the vehicle is lowered. The deck crew steps back. The winch pays out cable. The surface closes over the frame, and for a while the ROV passes through familiar water. There is still green light. There are plankton, bubbles, maybe the quick reflection of a fish near the ship. The pressure is already growing, but the world still resembles the ocean most people imagine. It is not yet the place where metal would collapse. It is the upper skin of the ocean, a moving boundary full of photosynthesis and weather, where sunlight still builds the food that will eventually fall into darkness. Below about 200 meters, ordinary photosynthesis no longer works. Light still exists, but it is reduced to dim blue and green, a filtered remnant of the surface. Red light has already vanished. Colors change because the wavelengths that reveal them are gone. A red shrimp may appear black. A black fish may disappear almost completely. This is the twilight zone, and it is not empty water. It is one of the busiest habitats on Earth, though it can look quiet when a camera passes through. Lanternfish, bristlemouths, shrimp, squid, siphonophores, jellyfish, and countless smaller animals live here in layers that rise and fall with the day. On sonar, these animals once looked like a false seafloor. The sound pulse left the ship, struck something below, and returned as if there were a solid boundary hanging in mid-water. Then that boundary moved upward at night, and downward again at dawn. The explanation was not a hidden bottom, it was life. Billions upon billions of small animals were making a daily migration, feeding higher in the dark and retreating deeper during the day, balancing hunger against the risk of being seen. In this layer, pressure is already far beyond what a human body can tolerate without protection. But for the animals, pressure is only one factor among many. Light, food, oxygen, temperature, and predators matter too. Some of the animals in the twilight zone use gas-filled swim bladders to control buoyancy, and that makes pressure part of their daily arithmetic. Gas compresses as pressure increases and expands as pressure decreases. For a fish that moves vertically through hundreds of meters, a gas space is useful but demanding. It must be regulated. Other animals reduce the problem by using oils, watery tissues, weakly mineralized bodies, or constant swimming. There is no single solution. The ocean is too large for that. Different lineages have solved buoyancy in different ways, and each solution comes with a cost that becomes visible only when the animal moves, feeds, hides, or dies. A trawl net brought up from this depth often lies. It may contain the animals, but not the world that shaped them. Soft bodies tear. Gas spaces expand. Eyes bulge. Stomachs turn outward. Colors fade. A fish that looked precise and controlled in the water can arrive on deck as a damaged object that seems stranger than it was alive. For centuries, some deep-sea animals were known mostly in that damaged state, lifted into air and interpreted after pressure had already rewritten them. The jar in the museum preserved a body, but it did not preserve the conditions that made the body make sense. This is one reason modern deep-sea footage matters so much. A camera does not solve the problem completely, because lights alter behavior and vehicles are loud, bright, and temporary. But footage lets scientists see animals before decompression, before drying, before the net and the deck and the jar. A ctenophore can show its comb rows moving in place. A squid can hold its arms in a posture that no preserved specimen would keep. A fish can hover with its fins barely moving, revealing that what looked grotesque in a photograph was functional in the water. The living animal corrects the damaged specimen. Below the twilight zone, the descent enters a darker pressure world. The midnight zone begins, where sunlight no longer guides ordinary vision. The water may be near freezing. Food is intermittent. The pressure has become high enough that any surface machine not built for it is already in serious danger. Yet the RUV light keeps finding bodies. A loose chain of salps. A transparent shrimp with red organs held inside it like a warning. A black fish whose skin swallows light. A medusa opening and closing with a rhythm too slow to feel urgent. The darkness is not empty. It is only less crowded per cubic meter than the surface and vastly larger in total volume. In the midnight zone, food arrives mostly by movement or by falling. Animals migrate down with full stomachs. Dead plankton sink. Fecal pellets descend. The soft remains of fish and squid fall out of the layers above. This sinking material is called marine snow, though it is not snow in the clean white sense. It is waste, mucus, shells, fragments, bacteria, dead cells, and small bodies. It is the slow afterlife of surface sunlight. By the time it reaches deeper water, much of its energy has already been eaten, recycled, or dissolved. What remains is still important enough to support entire communities waiting in the dark. A camera beam passing through marine snow makes the water look crowded with tiny falling stars. Each particle appears, flashes, and is gone. For a viewer at home, it can seem like atmosphere, like the texture of darkness. For an animal, it is food, or the sign of food. A sea cucumber on the abyssal plain will eventually process sediment enriched by these particles. A small amphipod may gather at a larger fragment. Bacteria begin work before larger animals arrive. Nothing is wasted quickly in the deep sea, but almost everything is contested, because energy is scarce and arrival is unpredictable. Pressure changes the engineering of bodies, but scarcity changes behavior. Many deep-sea animals move slowly because speed is expensive. Some wait instead of chasing. Some build large mouths because prey encounters are rare and a missed meal may matter. Some use bioluminescence not as decoration, but as a tool, a lure, a signal, a warning, a decoy, camouflage from below, or confusion in a pursuit. Light in the deep ocean is not the opposite of darkness. It is part of the darkness, produced by animals and bacteria in brief, controlled events. It does not illuminate the world the way sunlight does. It speaks across it. Consider the anglerfish, often shown as a symbol of deep-sea horror. In its own habitat, it is not a monster waiting for drama. It is an animal solving a problem. A female may carry a lure of glowing bacteria near her mouth because prey may be scarce and visibility almost absent. Her bones may be light. Her muscles may be reduced compared with active surface predators. Her stomach may expand because the next meal is uncertain. In some species, males are tiny and specialized for finding females in a vast dark water column. What looks grotesque on a poster becomes more understandable when seen as survival under pressure, cold, darkness, and distance. Even predation here has limits. A deep-sea predator does not live in a constant battle. It waits. It drifts. It fails. It passes through water where prey may be meters away, or hundreds of meters away, and where chasing the wrong signal can waste energy that took days to gather. A squid may flash and vanish. A shrimp may release a glowing cloud. A fish may hide its outline with counter-illumination, matching the faint, downwelling light above it. The pressure world is not only a place that crushes things, it is a place that punishes waste. And still, there are giants. Sperm whales dive into this world from above, carrying air in bodies built to manage pressure in ways humans cannot. Elephant seals descend through layers where our machines must be carefully sealed. Large squid live or pass through depths where the pressure would ruin ordinary metal compartments. The marks left on whale skin, the beaks found in stomachs, and the rare images of living squid show that the deep ocean is not simply a refuge for small, delicate forms. It also holds large predators and large prey, but their lives are difficult to observe because they move through a volume too dark and too wide for us to watch continuously. The evidence for much of this life is partial. A beak in a stomach does not show the hunt. A scar does not show the struggle. A single camera encounter does not reveal a daily pattern. A specimen in a net may show anatomy but not behavior. Scientists build understanding by combining these fragments: direct observations, stomach contents, chemical traces, genetics, acoustic data, environmental data, and the slow accumulation of dives. The pressure world does not refuse knowledge, but it releases it unevenly. It gives a few seconds of footage here, a damaged body there, a depth record, a signal, a pattern that becomes meaningful only after repetition. The ROV continues downward. The control room is dim, except for the monitors. Pilots speak in short sentences because the machine responds through a long tether, and every movement has consequences. The winch cable disappears into black water above them. On the screen, the depth number keeps changing. Outside, the pressure keeps adding itself to the vehicle. The lights show only a small room of water moving with the machine, and beyond that room is a volume so large that any single dive feels less like exploration of a place and more like a needle entering a planet. At 2,000 meters, pressure is about 200 atmospheres. At 4,000 meters, about 400. These numbers are simple to say and difficult to feel. A square inch at the surface carries about the weight of the air above it. Down here, every square inch of a housing carries hundreds of times that. A camera dome, a connector, a sealed battery case, and a sampling box all experience the force at the same time. If seawater finds a weakness, it enters with a violence that has nothing to do with waves. An implosion can destroy not only the failed part, but nearby instruments as well, because the surrounding water rushes inward and then rebounds. Deep-sea engineers sometimes avoid fighting pressure by allowing pressure in. This seems strange until you see the logic. A motor can be filled with oil so that water pressure is transmitted through the oil instead of crushing an air-filled cavity. Electronics, however, usually cannot be treated so simply. They need dry, protected spaces. That is why some parts are enclosed in pressure housings and others are pressure compensated. The vehicle becomes a mixture of resistance and acceptance. It fights the ocean only where it must. Everywhere else, it tries to make itself neutral, balanced, and less interesting to pressure. Animals have been following a version of that second strategy for far longer than engineers. They are not sealed vessels full of air. Many have flexible bodies that deform without catastrophic failure. Some have skeletons reduced to what is needed, not what would preserve well in a museum. Some gelatinous animals are so water-rich that the boundary between body and ocean seems almost negotiable. But they are not shapeless. A siphonophore is a colony arranged into a precise living structure. A jellyfish bell has muscle, nerve, and geometry. A transparent shrimp has limbs and eyes and a digestive system. Softness in the deep sea is not weakness, it is one kind of compatibility. A metal pipe lowered empty into the abyss is vulnerable because it insists on keeping a surface condition inside itself. A deep-sea jelly does not insist on that. It lives as water organized into life, with just enough structure to feed, move, reproduce, and respond. This is not magic. It is biology doing what engineering also tries to do, matching form to environment. The difference is that engineering must complete the match before launch, while evolution has been testing variations in the ocean for hundreds of millions of years, losing most of them, keeping a few, and modifying those few through lineages that never knew they were solving a problem. The seafloor does not arrive all at once. In many places, it rises first as a continental slope, a long descending margin cut by submarine canyons. These canyons are not just geological grooves. They can concentrate organic material, funneling food from shallower regions into deeper habitats. Currents move through them. Sediment slides through them. Carcasses and plant fragments can travel downslope. An ROV moving along a canyon wall may find corals, sponges, crabs, fish, and brittle stars, in numbers that surprise anyone who imagined the deep sea as a flat emptiness. Pressure is high here, but so is the possibility of food. Continental slopes can be productive because they connect surface systems to depth more directly than open abyssal plains do. A dead fish may settle on a ledge. A squid may drift into a current and be carried down. Particles falling from coastal waters may accumulate in pockets of sediment. Deep sea corals, unlike their shallow tropical relatives, do not need sunlight from symbiotic algae. They capture food from the water. Some grow slowly into branching habitats that shelter small animals. Their skeletons record years of chemistry and current conditions, becoming both habitat and archive in a pressure world where damage can last for a long time. These habitats also show why depth alone is never enough to explain the deep sea. Two places at the same depth can be very different if one is swept by current and another is still, if one receives frequent food falls and another receives little, if one has hard rock for attachment and another is loose sediment. Pressure sets the broad physical demand, but it does not write the whole ecosystem. Oxygen, temperature, chemistry, food, and geology shape what can live there. A fish hovering beside a canyon wall is living under pressure. Yes, but it is also living in a neighborhood defined by slope, current, prey, shelter, and risk. Seamounts create another kind of pressure world. They rise from deep water like submerged mountains, altering currents and gathering life around their flanks. Water moving against a seamount can bring suspended food to corals and sponges. Fish may gather where currents concentrate prey. Sharks, rays, tuna, and marine mammals may visit some seamounts, while deeper communities remain attached to rock in slow-growing forests of animals. The mountain itself may never break the surface. No beach, no cliff, no visible summit announces it to the air. But in the dark water, it changes the flow of energy, and life responds. Seamount communities can be vulnerable because the same features that gather animals can gather human attention. Trawls moving over deep coral can break structures that took centuries to grow. A net dragged across rock does not experience the habitat as a living forest. It experiences it as resistance. Broken coral branches, sponges, fish, and sediment come up together, and on deck the pressure world is reduced to weight. The damage happens in minutes. Recovery, if it happens, may take longer than the memory of the expedition, longer than the machines that caused it, longer than the careers of the people who measured it. Farther down, away from slopes and seamounts, the abyssal plain spreads across enormous areas of Earth. It can look like the simplest of worlds: flat sediment, drifting particles, an animal track, the occasional sea cucumber, a brittle star, a sponge standing alone on a stalk, a fish moving out of the beam. The simplicity is deceptive. The abyss is not rich in the way a reef is rich, but it is vast beyond ordinary imagination. 3/4 of the deep ocean floor lies within abyssal depths. Sparse life, multiplied across that area, becomes one of the largest living systems on the planet. On the abyssal plain, pressure may reach 400 to 600 atmospheres, depending on depth. Temperature is often near freezing. Food arrives mostly from above, slowly and unevenly. Sea cucumbers process sediment for organic matter. Brittle stars spread arms into the water or move across the bottom. Amphipods gather when a bait package lands. Xenophyophores, giant single-celled organisms, build delicate structures from sediment grains. Small tracks mark where animals have crossed, fed, or burrowed. The seafloor may appear still, but it is being reworked continuously by bodies that do not need to be large or fast to matter. When an ROV crosses abyssal sediment, the vehicle itself becomes an event. Its thrusters lift clouds from the bottom. Its lights strike animals that may never have encountered such brightness. Its weight and wash disturb a surface layer built slowly by falling particles. The pilots try to move carefully because the seafloor is not a blank floor under a machine. It is habitat. A small sea cucumber can be a recycler. A burrow can be a home. A patch of darker sediment can mark a food fall long after the visible body is gone. The pressure world keeps records, but they are written softly. This is also the world of manganese nodules, dark mineral lumps that form over extremely long timescales around small nuclei such as shell fragments or shark teeth. They may contain metals that humans find useful, including manganese, nickel, cobalt, and copper. To an industry, they can look like resources waiting on an open plain. To a biologist, they are also hard surfaces in a place where hard surfaces may be rare. Sponges, corals, anemones, microbes, and small animals can use them as anchor points. Removing the nodules removes not only minerals, but structure, and structure can be habitat. The deep sea has always seemed protected by distance, but distance is not protection once technology improves. A place can be remote and still be vulnerable. A machine built to survive pressure can become a mining tool as easily as a research tool. A camera that reveals a sea cucumber can also guide extraction. The pressure that once kept humans away is no longer a wall. It is a cost. And when a natural system grows slowly, receives food slowly, and repairs itself slowly, disturbance may remain visible long after the economic reason for the disturbance has changed or disappeared. None of this means the abyss is fragile in the sentimental sense, as though it were a glass ornament. It has endured earthquakes, landslides, volcanic ash, climate shifts, oxygen changes, and the slow rearrangement of ocean circulation. But endurance over geological time is not the same as indifference to disturbance. Life here is adapted to certain patterns of scarcity and pressure, not to repeated industrial scraping across wide areas. The difference matters. A pressure world can be physically severe and ecologically vulnerable at the same time. Then there are the places where pressure is joined by chemistry so extreme that the seafloor seems to be making its own weather. Hydrothermal vents appear where seawater enters cracks in the crust, is heated by magma, reacts with rock, and returns loaded with dissolved minerals and reduced chemicals. When that hot fluid meets cold deep water, minerals precipitate and build chimneys. Black smokers can release fluid hotter than boiling water at the surface, but at deep ocean pressure the water does not boil in the ordinary way. The pressure keeps it liquid while the chemistry turns it dark. A vent field can look like an industrial accident until the camera settles. Black fluid pours upward from a chimney. White bacterial mats spread over rock. Tube worms stand in clusters. Shrimp crowd near warm water. Mussels and crabs occupy cracks and edges. The fluid may contain metals and sulfides that would be toxic to many surface organisms. But the community is built around microbes able to use chemical energy. Here, sunlight is not the foundation. Chemosynthesis is. The food web begins with bacteria and archaea turning inorganic compounds into living matter, and animals arrange themselves around that invisible work. Pressure is essential to the vent world. Without it, the water emerging at such temperatures would behave differently. The high pressure allows superheated fluids to remain liquid and to carry dissolved materials from the crust. It also affects the animals living there, because vent organisms must tolerate not only depth, but steep gradients. A few centimeters can separate near freezing seawater from fluid hot enough to kill. A tube worm or mussel is not living in the black smoke or plume itself as if heat were harmless. It is living at the boundary, positioned where chemistry provides energy and temperature remains survivable. This is another place where the deep sea corrects simple imagination. Vent animals are not invincible extremophiles in the way the phrase is often used. Many are specialized for narrow conditions. Too far from the vent, the chemical energy declines. Too close, the heat and toxicity can be fatal. Their world is not uniformly hostile or uniformly generous. It is a shifting patchwork of flow, chemistry, rock, microbes, and larvae searching for a place that will not last forever. A vent field can shut down, a chimney can collapse, flow can move. The animals that seem fixed to stone are living with geological uncertainty. Metal behaves strangely in this environment too, not only because of pressure, but because of chemistry. Instruments lowered into vent fields return stained, corroded, crusted with minerals, or warmed beyond their ordinary design. Sampling arms must touch surfaces that are sharp, hot, and chemically active. A temperature probe entering black smoker flow is passing into water that would be impossible to hold in an open pot at the surface. The ROV is built for pressure, but the vent adds another layer of punishment. The deep sea does not have only one way to test a machine. At cold seeps, the drama is quieter. Fluids rich in methane or sulfide seep from the seafloor at temperatures close to the surrounding water. There may be no towering black plume, no chimney pouring smoke into the dark. Instead, the camera finds white microbial mats, beds of mussels, fields of clams, carbonate rocks, and sometimes tube worms rooted in sediment. The energy still comes from chemistry rather than sunlight, but the pace feels different. A seep can persist for long periods, feeding communities that grow around invisible release points where the earth leaks usable energy into the ocean. Mussels and clams at seeps often depend on symbiotic bacteria in their tissues. The animals provide access to chemicals, oxygen, and shelter. The bacteria produce organic matter from chemical energy. This partnership is not a curiosity at the edge of biology. It is a central strategy in some deep-sea habitats. Pressure does not prevent cooperation. It shapes the conditions under which cooperation becomes profitable. A clam bed at a seep may look still, but inside those shells, a chemical economy is running, connecting geology to microbes to animals to predators and scavengers, moving through the dark. Brine pools take the idea of a pressure world in another direction. In some deep basins, very salty water collects in depressions on the seafloor, becoming dense enough to form a lake beneath the sea. The surface between normal seawater and brine can ripple like a shoreline. A fish may swim above it. Mussels may crowd around the edge. The brine itself can be low in oxygen and rich in methane or hydrogen sulfide. To many animals, crossing into it is not like entering ordinary water. It is entering a chemical trap. ROV footage from brine pools can be unsettling because the scene looks familiar in the wrong way. There is a shoreline, but no air. There are waves, but they are waves between waters. A dead crab may lie partly submerged, preserved in a boundary it could not survive. A fish may approach and turn away. Microbial mats spread in pale bands. The edge of the pool becomes a line between possible and impossible habitats, and the pressure above it makes the whole scene more difficult to place in ordinary thought. It is a lake in darkness, under thousands of meters of ocean, and it has its own coast. Not every animal near a seep or brine pool is a specialist. Some are visitors drawn by food or structure. Crabs may feed among mussels. Fish may patrol the edge. Shrimp may gather where microbes grow. Predators and scavengers connect these chemical habitats to the wider deep sea, carrying energy away from the source. This matters because vents, seeps, whale falls, woodfalls, and carcasses are often described as islands, and the metaphor is useful, but not complete. Islands have traffic. Larvae disperse. Scavengers arrive and leave. Nutrients leak outward. The pressure world is patchy, but the patches are not sealed. A whale fall is one of the clearest examples. At the surface, a whale is an animal of air and sunlight, surfacing to breathe, diving to feed, moving through currents with a body warmed by metabolism and insulated by fat. When it dies, the same body becomes a descending event. It may drift for a time. Sharks may feed. Gases may bloat it. Then it sinks, slowly or suddenly, into water where pressure rises around it and light disappears. By the time the carcass reaches the seafloor, it is no longer only a dead whale. It is a concentrated delivery of energy to a place where energy is rare. The first animals to arrive are often mobile scavengers. Hagfish enter the body and feed from within. Sharks may tear soft tissue. Amphipods, crabs, isopods, and fish gather around the edges. The seafloor becomes disturbed with movement. Sediment clouds rise. Flesh disappears in stages, not as a single clean event, but as a long feeding process. A camera returning months later may find bones where a body once lay, and the bones are not empty. They hold lipids. They hold structure. They invite a second community, smaller and more specialized, to begin its work. Whale falls can support succession. After mobile scavengers remove much of the soft tissue, sediments enriched by organic fragments feed worms, crustaceans, and microbes. Later, bacteria break down compounds in the bones, producing sulfide that can support chemosynthetic communities. Bone-eating worms, including Osedax, bore into the skeleton and use symbiotic bacteria to access nutrients inside. The whale becomes habitat, food source, chemical reactor, and reef-like structure. In the deep sea, a single death can feed life for years, and in some cases the skeleton may remain biologically important for much longer. Pressure does not stop this afterlife. It contains it. The carcass does not rot the way it would on a warm beach. Cold slows decay. Darkness removes visual spectacle. The surrounding water presses on every cavity. Gases behave differently as depth increases. The animals that come to feed are not performing a grim exception to life. They are carrying out one of the deep ocean's ordinary processes, turning rare abundance into bodies, eggs, bacteria, sediment chemistry, and future movement. The whale's surface life ends, but its material continues downward into another food web. Sometimes the evidence of this system is not a whale at all, but a bone, a fragment, a jaw, a vertebra, carried in a manipulator claw and placed into a sample box. In the laboratory, researchers may examine the worms, the bacteria, the isotopes, the small animals living in cavities. The pressure world has been brought upward, but only in pieces. Some animals survive the trip poorly or not at all. Some relationships are easier to infer than to watch. The story of a whale fall is therefore built from visits, samples, photographs, and the patience to return to the same dark place again and again. Deeper still are the trenches, where the ocean floor bends downward into long, narrow scars at the edges of tectonic plates. Below 6,000 meters, the hadal zone begins. Its name comes from Hades, but the place should not be treated as an underworld in the mythic sense. It is a real habitat with walls, slopes, sediment, currents, microbes, amphipods, worms, sea cucumbers, and fish in some trenches. It is not one continuous basin encircling the planet. It is a set of isolated deep places, each with its own geography and history, separated by shallower abyssal regions that may be barriers to many species. At hadal depths, pressure reaches levels that are difficult to translate into ordinary experience. At 11 kilometers, it is roughly 1,100 times the pressure at sea level. Full ocean depth vehicles are not ordinary submarines with extra metal added. They are specialized machines where every window, seal, sphere, thruster, battery, and flotation material must be chosen for survival under compression. A human cannot step outside. A thin-walled air-filled object cannot remain intact. Even strong metals can fail if the shape, thickness, or material condition is wrong. The trench is not trying to crush anything. It is simply applying the physics of depth without interruption. Yet animals live there. Hadal snailfish have been filmed in trenches, moving with pale flexible bodies over baited landers and sediment. Amphipods gather in great numbers around food. Microbes process organic matter that funnels down trench slopes. Some hadal animals contain molecules that help stabilize proteins under pressure, and researchers continue to study how their membranes and cellular machinery function where shallow water cells would struggle. These animals are not deep-sea superheroes. They are specialists. Bring them upward too quickly, and the pressure world they require disappears around them. A hadal lander descends without a pilot, falling through water under its own weight, carrying cameras, lights, bait, and instruments. It may take hours to reach the seafloor. There is no cable reaching all the way down in many designs, no live control from the ship, only programming and patience. When it lands, the lights illuminate a small patch of sediment. Amphipods arrive first, often so many that they fill the frame. Then perhaps a fish appears at the edge, pale and soft-bodied, touching the bait, turning with a motion that seems unhurried because the whole world around it is cold, dark, and compressed. The trench is a pressure world where human imagination often goes too quickly to extremes. It is easy to say crushing, deepest, alien, impossible. It is harder and more useful to say that food arrives by sinking and sliding, that species may be isolated by trench geography, that pressure affects proteins, that sediment can accumulate organic material, that animals still compete, feed, avoid, reproduce, and die. The deepest places are not beyond ecology. They are ecology under conditions that demand unusual solutions. Pressure also affects the tools of measurement. A sensor that works at 1,000 meters may not work at 10,000. Conductivity, temperature, and depth instruments need correction. Batteries behave differently. Acoustic communication becomes essential but limited. A camera housing must survive both descent and ascent. A sample taken from the trench may change during recovery unless it is kept under pressure, and maintaining pressure from seafloor to lab is one of the hardest problems in deep-sea biology. The act of observing can remove the condition being observed, and that is why some knowledge remains difficult even after the camera sees the animal. The same is true at less extreme depths. A deep sea comb jelly brought to the surface may not behave as it did below. A fish adapted to cold and pressure may lose normal function when warmed and decompressed. A soft animal may collapse under its own unsupported shape in air. The surface is not neutral. It is an environment too, and for many deep animals, it is a hostile one. To study the deep sea well, scientists must remember that the deck of the ship is not the place where the animal's body was meant to make sense. This is why pressure-retaining samplers and laboratory pressure systems are so important. They allow researchers to bring microbes, small animals, or chemical samples upward while preserving more of the physical condition from depth. They are difficult to build because they must do two opposite things: open at depth to collect, then close strongly enough to hold pressure during the return. They must also avoid contaminating samples, damaging organisms, or changing temperature too much. Each successful sample is not simply a jar of water or mud, It is a small captured fragment of a pressure world, held temporarily against the surface. In a dark laboratory, that fragment may reveal processes no camera can show. Microbes may change their metabolism under different pressures. Proteins may fold or fail. Membranes may become too stiff if the pressure and temperature are wrong. A tiny animal may swim normally only when the chamber is set to something like its home depth. These experiments do not replace dives, they extend them. The ROV shows where the animal lives. The pressure chamber helps explain how living there is possible. The deeper the subject goes, the more the word collapse changes meaning. Metal can collapse mechanically, a hollow sphere can implode, a vehicle can fail. But a biological system can collapse in other ways. Remove pressure, and proteins may stop behaving as expected. Remove cold, and metabolism changes. Remove darkness, and behavior changes. Remove food input from above, and the seafloor changes. Remove hard substrate from an abyssal plain, and animals that used it lose habitat. Collapse in the deep sea can be sudden and violent, or slow and ecological, visible only after repeated measurements reveal what is missing. It is tempting to imagine that pressure alone explains the strange forms of deep-sea animals, but that would be too simple. Many features that people associate with depth are responses to darkness, food scarcity, predation, or reproduction rather than pressure directly. Large eyes help in dim light, but not in total darkness. Transparent bodies reduce visibility. Red coloration can appear black where red light is absent. Enlarged jaws help with rare prey encounters. Slow growth may reflect cold and low food. Gelatinous tissues can help with buoyancy and energy savings. Pressure is always present, but it is only one part of the selection landscape. Still, pressure sets boundaries. It determines what kind of gas spaces are practical, what machinery survives, how cells must maintain function, and which animals can move between depths. A shallow water fish cannot simply choose to live in a trench. A trench animal cannot simply choose to live at the surface. Vertical ranges exist, and some are narrow, others are broad. Migrating animals cross pressure gradients every day, but they do so with bodies adapted for that crossing. Life can be flexible, but not infinitely flexible. Every body carries the history of the pressures it can tolerate. In the control room, pressure appears as numbers and engineering limits. On the seafloor, it appears as the absence of things humans expect. No open air, no loose foam, no ordinary glass sphere, no empty lung, no casual repair by a diver in a wetsuit. Everything must either be built for the pressure, filled so pressure can pass through it, or left behind at the surface. A deep-sea animal does not read the number on the monitor. It feels no drama in 4,000 meters. Its body has no memory of sea level as a home. This is one of the most important differences between exploration and habitation. Humans visit the deep sea as an event. Animals live there as a condition. A submersible dive has a launch time, a bottom time, a recovery, a maintenance schedule, a team, and a cost. A rat tail above the sediment has no mission clock. A sea cucumber crossing abyssal mud is not in an extreme environment from its own point of view. A snailfish in a trench is not surviving a stunt. It is occupying the only world its lineage has made available to it. The language of extremes can make deep sea life sound like a performance. Crushing pressure, total darkness, freezing water, alien creatures. These phrases are not always wrong, but they can tilt attention towards spectacle and away from ordinary biological work. The animals are not trying to astonish us. They are feeding, avoiding being eaten, finding mates, producing eggs or larvae, healing injuries, following chemical gradients, responding to current, and using energy carefully. The deep sea is strange because the rules are different from ours, not because the animals have escaped rules. One practical rule is that pressure increases predictably with depth. Another is that food generally decreases with distance from the sunlit surface, except where chemistry, geography, or carcasses create local abundance. Another is that cold slows many processes, though not all. Another is that oxygen can become limiting in some layers and regions. The oxygen minimum zone, for example, can compress where animals live by making certain depths difficult for active metabolism. Some species tolerate low oxygen, others avoid it. The vertical structure of the ocean is therefore not just light on top and darkness below. It is a stack of overlapping constraints. A small squid moving through an oxygen-poor layer is crossing more than a depth boundary. It is crossing a physiological challenge. A fish with low metabolic demands may occupy water that would exhaust a faster predator. A crustacean may reduce activity until conditions improve. Predation changes where oxygen changes. Migration routes change. The deep scattering layer may shift. A camera lowered through these zones may see only scattered animals, but the distribution is not random. It reflects invisible lines in the water, some chemical, some physical, some biological, all interacting with pressure as the constant background. Climate change reaches these pressure worlds indirectly, but seriously. Warming at the surface can alter stratification, oxygen, productivity, and the amount and quality of food sinking downward. Deoxygenation can expand low oxygen zones. Changes in currents can change where particles travel. Acidification can affect shells and skeletons. The deepest animals may never see sunlight, but they are not disconnected from the surface. Marine snow is a message from above. So is plastic. So are pollutants. So are changes in the timing of plankton blooms. The pressure world is hidden, not isolated.
This connection matters because deep-sea animals often live slowly. Some grow slowly. Some reproduce infrequently. Some live in habitats where recovery from disturbance is limited by larval supply, substrate, food, and time. A cold water coral broken by a trawl may not be replaced in a human lifetime. A nodule field stripped of nodules may not regain that structure for millions of years. A vent community may recover differently depending on flow and larvae. The deep ocean can seem too large to damage, but damage does not need to affect the whole ocean to matter. It only needs to erase a habitat that took longer to form than we took to find it. In many deep-sea videos, the most important thing is not the rare animal in the center, but the frame around it. The particles falling, the sediment texture, the distance to the next rock, the absence of obvious cover, the way an animal turns away from light, the way a manipulator arm pauses before touching something because the pilot knows the touch is an intrusion. A pressure world reveals itself through small details. Not every descent ends with a new species, a giant squid, or a vent field. Many end with careful records of ordinary life in a place almost no one has seen. Ordinary deep-sea life is still difficult to measure. Biomass estimates require nets, acoustics, cameras, models, and assumptions. Species ranges may be known from a handful of specimens. Behavior may be inferred from anatomy. Reproduction may be unknown for animals that have been named for decades. Some species are common in trawls but rarely filmed alive. Others are filmed repeatedly but almost never collected. The deep sea is not unknown in an absolute sense. It is known unevenly, with bright points of evidence separated by very large gaps. Scientific restraint is important here. A single observation of an animal feeding does not prove what it always eats. A maximum depth record does not define its preferred habitat. A specimen damaged by collection does not represent its living appearance. A strange posture may be a normal behavior, a response to lights, or a stress reaction. Researchers often have to speak in probabilities because the honest answer is rarely complete. The deep sea does not reward certainty given too early. It rewards patience, repetition, and instruments that survive long enough to return data. Sometimes the instrument is as interesting as the animal because it makes the observation possible. A baited camera lands on the seafloor and waits. A time-lapse system watches sediment change. A CTD rosette lowers bottles through different depths, collecting water for chemistry and environmental DNA. A sonar maps a canyon in lines and returns. A pressure-retaining sampler closes around microbes. A robotic arm lifts a rock, clips a coral, or places a marker beside a vent. Human presence in the deep ocean is usually mechanical presence, and every machine is a compromise between what scientists want to know and what pressure allows them to bring. A pressure housing on an ROV may seem like a minor part of a larger mission, but it is the difference between sight and blindness. Inside that housing is a camera, a computer, a memory system, or a power connection that cannot be exposed directly to seawater. Outside is pressure that will exploit any weakness. The housing may be made of titanium, aluminum alloy, glass, ceramic, or composite material, depending on depth and use. It may be tested in a pressure chamber before it ever reaches the ocean. Failure there is disappointing. Failure at depth can mean losing a mission, a vehicle, or years of work. The same is true for human-occupied vehicles. A person going to depth is enclosed inside a pressure hull, often a sphere because the geometry distributes compression evenly. The hull must be strong, but also not too heavy to recover.
It must have viewports, penetrators, life support, controls, and emergency systems.
The vehicle must sink, maneuver, and return. It must be buoyant enough to come back even if something goes wrong. Deep ocean engineering is not just about resisting pressure. It is about returning from pressure with people, samples, and data intact.
Alvin, Deep Sea Challenger, Limiting Factor, and other deep vehicles are names attached to this narrow human ability to enter pressure worlds briefly. Their dives are remarkable because the ocean does not make room for them. Every descent is negotiated by design. A pressure hull is not heroic in the theatrical sense. It is precise. It is measured. It is built so that no part carries more stress than intended, so that the shape remains close enough to perfect, so that the ocean's force is spread rather than concentrated. The drama is not only in reaching the bottom, it is in the fact that the sphere remains a sphere. For animals, no launch ceremony marks the beginning of life at depth. Eggs drift. Larvae settle. Juveniles grow. Some animals rise and fall each night. Others remain near the bottom for their entire lives. Some deep-sea species may have larval stages that travel far from the adults, crossing currents and chemical gradients before finding the right habitat. A vent mussel begins as something small enough to be carried by water through darkness. Its future depends on reaching a place where the chemistry, temperature, substrate, and pressure all permit its body to continue. Reproduction in the deep sea can be hard to observe. For many animals, scientists know the adult form better than the life cycle. Eggs may be rare in footage. Larvae may be difficult to identify. Mating may never have been filmed. Some deep-sea octopuses brood eggs for long periods in cold water, guarding them without feeding much or at all. Some fish release eggs into the water column. Some invertebrates broadcast larvae that must find rare habitats across enormous distances. Pressure does not remove the ordinary problems of reproduction. It makes them occur in a world we can barely watch. A deep-sea octopus on a slope can look almost weightless. Its arms spread over rock. Its skin changes texture. Its body compresses and expands slightly with movement, not because pressure is changing at that moment, but because soft tissues are working in cold darkness. Some octopuses have been seen brooding eggs near warm seepage, where slightly higher temperatures may shorten development. That kind of detail matters. It turns a strange animal into a parent making use of a specific habitat. It shows that deep sea life is not only adapted to pressure in a general way, it is also adapted to small opportunities within pressure. Parenthood in the deep sea can carry heavy costs. Long brooding means long vulnerability. Eggs develop slowly in cold water. A guarding adult may lose condition over time. Predators and scavengers continue moving through the habitat. Sediment can shift. Oxygen can vary. A camera may find the animal once and return months later to a scene changed beyond easy interpretation. The deep sea does not pause for observation. It continues between visits, and much of what matters happens when the lights are gone. Time itself behaves differently in the way humans perceive these environments. The pressure does not make time slower, but cold, scarcity, and darkness often produce biological rhythms that feel slow compared with surface systems. Growth rings in corals can record long histories. Sponge communities may persist across decades or centuries. Sediment accumulates grain by grain. Tracks remain until erased by current, animal movement, or another fall of material. A dead fish can become a temporary center of activity. A whale skeleton can structure a community over years. The deep sea is not frozen. It is active at scales that punish impatience. This slower pace is why ROV footage can feel uneventful at first. The camera moves. Particles fall. A fish drifts away. A crab walks out of view. But if you stay with the frame, patterns begin to appear. The fish is holding in current, not floating aimlessly. The crab is following a scent trail. The sediment has small holes and ridges. The sponge is not alone. Tiny animals cling to it. A brittle star lifts its arms when particles pass. What seemed empty becomes organized, and the organization becomes the evidence that the pressure world is inhabited, not merely endured. Many deep-sea fish have reduced bones and watery muscles compared with shallow, fast-swimming species. This is partly about energy. Heavy skeletons and powerful muscles are expensive to build and maintain. In a world where food is sparse, an animal that can remain neutrally buoyant and move economically may have an advantage. Some species have large heads and jaws relative to body size. Some have sensory pores and lateral lines tuned to movement in darkness. Some have small eyes, because light is useless where they live. Others have large tubular eyes in the twilight zone, where faint light and silhouettes still matter. The diversity of forms reflects the diversity of problems. A hatchetfish with photophores along its belly is solving one problem, hiding its silhouette from predators below by matching downwelling light. A tripod fish standing on elongated fin rays above the sediment is solving another, waiting in current for small prey to pass. A gulper eel with a huge mouth is solving another, making the most of rare encounters. A sea pig moving across abyssal mud is solving another, harvesting organic matter from sediment. These animals are often grouped together as deep-sea creatures, but they are not variations on a single idea. They are different answers to different conditions. The pressure world is therefore not one world, but many stacked and scattered through the ocean. Twilight layers full of migrating animals. Midnight water, where bioluminescence replaces sunlight as a signal system. Continental slopes cut by canyons. Seamounts lifting hard rock into currents. Abyssal plains stretching across ocean basins. Vents where chemistry feeds dense communities. Seeps where methane and sulfide leak quietly into sediment. Brine pools with underwater shorelines. Whale falls that turn death into habitat. Trenches where the weight of the ocean reaches its greatest force. Each is connected to the others, but each has its own rules. Metal would not collapse in all of these places in the same way. A properly designed titanium sphere may survive where an ordinary steel box would fail. A pressure-balanced motor may function where an air-filled motor would implode. A thick glass sphere may endure if it is flawless and shaped correctly. But the phrase points to a real boundary. At depth, strength is not a general property. It is specific to geometry, material, thickness, manufacturing, testing, and use. The ocean does not respect the idea of metal as automatically strong. It asks what shape the metal takes, what emptiness it encloses, and where the weakness begins. A sealed soda can crushed in a demonstration is not the same as a deep ocean implosion, but it gives a small hint. When pressure outside greatly exceeds pressure inside, the walls no longer carry the load successfully. They buckle inward. At greater depths and larger scales, the energy involved can be enormous. In deep sea work, implosion is not a metaphor. It is a known hazard. That is why housings are tested, ratings are respected, and engineers do not casually send unproven containers into deep water. The descent may look smooth on a monitor, but every meter is another test. Animals do not pass this test by being harder than metal. Many are softer than anything a human would call strong. They pass because the pressure is not trying to crush a difference. Their tissues and fluids are already under pressure. Their internal chemistry is arranged to work there. Their membranes remain functional. Their proteins remain useful. Their body spaces avoid dangerous gas expansion or compression. A jelly in the midnight zone is not resisting the ocean with a wall. It is living as a form that does not need one. This distinction changes how the deep sea should be imagined. The greatest pressure worlds are not places where life defeats physics. They are places where life has become compatible with physics. A hadal amphipod is not stronger than a submarine. It does not need to be. It has no pilot sphere, no viewport, no air compartment, no need to keep a human breathing at 1 atmosphere. It needs enzymes, membranes, muscles, nerves, and reproductive cells that work in a different pressure range. That is a more subtle achievement than armor, and perhaps a stranger one. Scientists studying deep pressure adaptation have found that some deep animals use chemical compounds that help stabilize proteins under pressure. Trimethylamine N-oxide, often called TMAO, is one of the best-known examples in fishes, increasing in concentration with depth in many species. But even this pattern has limits and complications. It is not a single magic ingredient that explains all deep life. Different animals use different biochemical strategies, and the deepest depths may impose constraints that help define where certain groups can live. The biology of pressure remains an active field because the solutions are molecular, varied, and hard to observe in living animals. The deeper a fish lives, the more difficult it may be to keep its proteins working properly, but it must also keep its body from becoming too energetically expensive. Biochemical protection has a cost. Membrane composition has a cost. Slow growth has a cost. A deep sea body is a budget written in tissue. Nothing is free simply because the environment is extreme. The animal must still gather enough food to build itself, maintain itself, avoid damage, reproduce, and leave descendants. Pressure adaptation is not separate from ecology. It is part of the same accounting. A snailfish filmed in a trench does not look like a conqueror of pressure. It looks pale, soft, almost delicate. Its fins ripple, its head lowers toward bait. Amphipods scatter around it. The scene is lit by an instrument that had to be engineered to survive the descent, yet the fish moves through the frame as though the crushing depth were ordinary. For the fish, it is ordinary. The extraordinary part belongs to us, watching from a ship or a screen, trying to reconcile softness with 11 kilometers of water above it. This is the repeated lesson of the deep ocean. Human intuition is trained by air. We think of strength as rigidity, survival as resistance, and danger as something visible approaching from outside. The deep sea teaches a different set of intuitions. Flexibility may be strength. Openness to pressure may be safer than sealed emptiness. Darkness may be a communication medium, not only an absence. Scarcity may favor patience over aggression. A place that looks empty may be enormous enough to contain more life than a crowded frame could suggest. The camera beam is narrow. The ocean is not. A typical ROV dive samples a tiny path through a huge three-dimensional habitat. Even a long expedition covers little compared with the volume of the deep sea. This is why scientists are careful with statements about rarity. An animal may be rarely seen because it is truly rare, or because it lives away from the paths we sample, avoids lights, occupies depths we visit less often, or appears only at certain times. The absence of footage is evidence, but weak evidence unless the search effort is known. The deep sea can hide common things simply by being large. Environmental DNA is changing part of that problem. By filtering seawater and analyzing genetic fragments shed by organisms, researchers can detect species or groups that may not appear on camera or in nets. The method has limits. DNA moves. It degrades. It may not reveal abundance or behavior, but it adds another layer of evidence, especially in habitats where direct observation is expensive or brief. In a pressure world, even traces matter. A few molecules in a water sample can suggest that an animal passed through the darkness before the machine arrived. Acoustics offer another kind of indirect vision. Sound travels far in water, and sonar can reveal layers, schools, seafloor shape, and sometimes animals that cameras never see. The deep scattering layer was understood in part because sound returned from living bodies. Multi-beam sonar maps can show canyons, ridges, pockmarks, landslides, and trench walls before a vehicle descends. Acoustic releases allow landers to drop weights and return. Communication with deep vehicles may depend on sound when cables are absent. The pressure world is dark to human eyes, but it is not unreachable to measurement. Still, there is something irreplaceable about the first visual contact with a place. The map shows a slope. The camera shows a fish lifting from it. The chemical sensor shows methane. The camera shows mussels around a seep. The depth reading says 4,000 meters. The camera shows a sea cucumber leaving a track in sediment that has not seen sunlight for longer than human history. Visual evidence is not the only evidence, but it anchors imagination. It reminds us that every line on a chart is also a place where animals are living. Sometimes the visual evidence is a warning. A plastic bag caught on a deep coral, a fishing line wrapped around sponge branches, a beer can on the abyssal plain, a tire near a canyon wall. These objects survive pressure better than they deserve to. They arrive as evidence that the surface world has entered the pressure world without understanding it. Unlike a carcass, they do not become food in a useful way. Unlike a nodule or bone, they did not form through the slow processes of the habitat. They are artifacts of carelessness, and the deep sea keeps them, because cold and darkness can preserve what we would rather forget. Pollution is not dramatic in the same way as an imploding pressure housing, but it is part of the same story of contact. The deep sea is no longer beyond human reach. It receives our instruments, our samples, our cables, our fishing gear, our noise, our carbon, our trash, and perhaps soon more mining equipment. Some contact expands knowledge. Some contact extracts. Some contact harms by accident. The pressure world is not asking to be untouched in any simple sense. Science must touch it to understand it. But touch can be careful or careless, limited or expansive, curious or hungry. In the reference frame of the animal, none of this is philosophical. A crab finds food. A fish avoids light. A worm enters bone. A mussel opens slightly in the current. A snailfish follows scent. A coral polyp captures particles. Life continues through small acts that do not require our attention. The deep sea existed before cameras, before pressure ratings, before ships with dynamic positioning, before titanium spheres and syntactic foam. Our machines did not create the pressure world, they only made it briefly visible to us. The deepest ocean is not uniformly cold everywhere in a simple way, but much of it is near freezing. Temperature matters because chemical reactions and biological rates respond to it. Cold water can hold more oxygen than warm water, but oxygen availability still depends on circulation and consumption. In some basins, oxygen is plentiful enough for active animals. In others, oxygen minimum zones create constraints. Hydrothermal vents and seeps introduce local heat or chemistry. Brine pools introduce salinity and toxicity. The physical environment of the deep sea is therefore layered, regional, and dynamic, even when the camera sees only black water. It is also not true that deep-sea animals never experience change. Seasonal pulses of marine snow can follow surface blooms. Storms can alter the material reaching slopes and canyons. Earthquakes can trigger turbidity currents, sending sediment and organic matter downslope in powerful underwater flows. Vent flow can change. Seepage can strengthen or weaken. A whale can fall. A large carcass can create abundance in a small area. The deep sea is buffered from daily weather, but not from all variability. Its changes are often delayed, transformed, or hidden, not absent. A turbidity current is one of the more powerful reminders that the deep seafloor can move. Sediment-laden water rushes downslope like an underwater avalanche, carrying mud, sand, organic matter, and sometimes broken life with it. It can snap cables, reshape channels, and bury habitats. To an animal on the seafloor, this is not a distant geological process. It is a sudden change in the world. The pressure remains the same, but the bottom itself is rewritten. When scientists later map the canyon or recover damaged equipment, they are reading the aftermath of a deep event no one watched directly. The idea of metal collapse becomes almost modest next to the scale of the ocean's own forces. Pressure is one force. Gravity-driven sediment flows are another. Tectonic plates bend and fracture. Vents build and fail. Trenches deepen over geological time. The ocean floor records impacts, landslides, ash falls, currents, and chemical deposits. Human machines enter this moving system with the illusion of control because they are carefully engineered and watched from a ship. But the machine's control is local and temporary. The ocean's control is planetary and continuous. And yet, the smallness of the machine is what makes its footage valuable. A light on a vehicle does not reveal the whole deep sea. It reveals one place at one time. A shrimp on a vent chimney. A sea cucumber crossing a plain. A fish beside a bait package. A coral branch growing from rock. A line of amphipods at a carcass. Each view is partial, but partial views accumulate. The deep ocean becomes knowable not through one grand unveiling, but through thousands of careful descents and recoveries, each one adding a few more facts to a world too large for any single story. Long-form deep-sea narration should resist the temptation to turn every unknown into mystery for its own sake. Some things are unknown because they are difficult to observe, some because funding is limited, some because animals are rare or widely dispersed, some because their bodies do not survive collection, some because the relevant process happens at microbial or molecular scales. Mystery is real, but it is not a substance filling the ocean. It is the boundary between current evidence and the next observation. That boundary moves when instruments improve. Over the last several decades, the boundary has moved many times. Hydrothermal vents were first observed in the late 20th century and changed ideas about where complex ecosystems could get energy. Cold seeps revealed additional chemical habitats. Whale falls showed how large carcasses structure communities. ROVs and AUVs have mapped canyons, seamounts, and trenches with increasing detail. High-definition cameras have made living animals visible in their own posture and color. pressure-retaining tools have allowed more realistic study of deep organisms. The hidden ocean remains hidden in large part, but it is less hidden than it was. New discoveries often refine rather than overturn. A new species of deep-sea fish adds detail to a lineage. A vent animal found beneath the seafloor extends the known habitat into cracks and cavities. A repeated observation of a behavior turns an anecdote into a pattern. A map shows that a canyon is more complex than expected. A genetic analysis reveals that two similar-looking animals are separate species. This is how the pressure world becomes scientifically clearer, not by losing all strangeness, but by gaining structure. Structure also means limits. A trench species may not be able to cross into another trench if the abyssal plane between them is too shallow, too warm, or chemically different. A vent species may depend on larvae finding another active vent before the first one fades. A coral species may need hard substrate and sufficient current. A midwater predator may depend on the depth range of migrating prey. These dependencies make deep-sea animals less like symbols of resilience and more like organisms with specific requirements. They can tolerate what would kill us, but they may be unable to tolerate what seems mild to us. This is why bringing deep animals to the surface can be a kind of violence even when done for science. The pressure drops, temperature rises, light changes, handling begins. The animal enters air or shallow water, and the body that worked below begins to fail or distort. Scientists know this, and modern methods try to reduce it, but the problem remains. The surface is where humans can work easily. The deep is where the animals are themselves. Every specimen is therefore both a source of knowledge and a reminder of the distance between collection and life. A preserved deep sea fish in a museum jar may have cloudy eyes, pale skin, a slack mouth, and fins pressed close to its body. It may not look like the animal that moved through black water. But the jar still matters. It preserves bones, teeth, scales, fin rays, stomach contents, reproductive organs, and DNA if conditions allow. It can be re-examined decades later with tools its collectors never imagined. The deep sea is known through living footage and dead specimens together. Neither is complete alone. The jar tells one truth. The camera tells another. A museum drawer and an abyssal plane are connected by acts of recovery. A small label may carry coordinates: depth, date, ship, gear, and collector. Those details are not decoration. They are how the specimen remains attached to a place. Without them, it becomes an odd body without a world. With them, it becomes evidence of a habitat, a pressure range, a community, a moment in exploration. The deep sea is difficult to know partly because context is so easy to lose. A fish without depth is almost a sentence missing its subject. Depth ranges matter because pressure scales with them. But pressure is not the only reason. Light, temperature, food, oxygen, and predators all change with depth. A species recorded between 500 and 1,000 meters is living in a different set of conditions than one recorded between 3,000 and 4,000. A trench specialist below 8,000 meters occupies another set again. These ranges help scientists understand distribution and adaptation, but they must be interpreted carefully. A capture depth may reflect where the net closed, where the animal was caught, or where it was carried. Nets have their own biases. Fast animals can avoid them. Fragile animals can be destroyed by them. Gelatinous animals can pass through or be shredded. Midwater trawls sample a volume, but not always with fine precision. Bottom trawls collect from a path, but disturb the habitat. Cameras have different biases. They see only what passes in front of them, and their lights may attract or repel. Baited cameras attract scavengers and predators, but not necessarily the wider community. Every method changes the view. The best picture comes from combining imperfect views and knowing how each one is imperfect. The pressure world is not offended by our methods. It simply responds according to its conditions. A bait package releases odor into the current, and amphipods follow. A light shines, and some animals withdraw. A manipulator arm lifts sediment, and a cloud forms. A lander hits the bottom, and the seafloor receives a sudden object from above. Observing the deep sea is always an intervention, but not all interventions are equal. Careful science makes the disturbance small, records it honestly, and learns without pretending to be invisible. The pressure never stops. It is there during the launch, descent, observation, sampling, and recovery. It is there after the ship leaves. It presses on the vent chimney, the whalebone, the amphipod, the pressure housing, the camera lens, the sediment pore water, the eggs of a fish, the microbial film on a rock. It does not pulse with drama. It does not pause for an important moment. It is the most consistent character in the deep sea, and because it is so consistent, animals can adapt to it. Catastrophe is often not pressure itself, but a sudden change away from the pressure range a body or machine was built to know. For a machine, sudden change can happen during ascent too. A housing that survived depth still must survive the return. Seals must keep water out as external pressure drops. Samples may degas. Temperature changes. A pressure-retaining chamber must hold its internal pressure while the outside becomes easier. In human terms, ascent feels like relief. In engineering terms, it is another phase of stress. In biological terms, it may be dangerous if not controlled. The journey upward is not simply undoing the journey downward. It is its own experiment. The ship's deck, after a deep dive, can feel almost too bright. People gather around the vehicle. Salt water drains from the frame. Samples are passed to the lab. A rock from a vent, a tube of sediment, a jar of water, a coral clipping, a piece of bone, a small animal in chilled seawater. Each object has crossed a boundary that most life never crosses. Some will be photographed, some will be preserved, some will be kept cold, some will be placed in pressure systems if possible. The deep sea arrives in fragments, and the surface tries to keep them meaningful. Inside the lab, the fragments lose some of the darkness, but not all of their significance. Sediment cores are sliced in layers, microbes are cultured or sequenced, tissue samples are taken, shells are measured, bones are examined for borings, water chemistry is analyzed. A small label follows each sample because without location and depth, the sample is half lost. The pressure world has been reduced to data points and containers, but those data points are how the next descent becomes better aimed. This cycle of descent, observation, recovery, analysis, and return is how many deep sea facts become stable. One dive may reveal an unexpected animal. A second dive may show it again. A sample may confirm its identity. A genetic comparison may place it among relatives. Environmental measurements may define the conditions where it lives. Over time, the animal becomes less of a mystery and more of a species with a range, behavior, anatomy, and ecological role. The wonder does not disappear when the facts improve. It becomes less vague and more durable. There is a quiet satisfaction in that kind of knowledge, not the thrill of declaring the deep sea unknowable, but the slower satisfaction of learning one more true thing about it. That a shrimp species clusters at a particular temperature boundary. That a coral grows where current delivers food. That a snailfish can live deeper than most bony fish. That a whale skeleton supports different communities over time. That a metal housing must be spherical, or thick or pressure balanced to survive where a soft animal moves normally. These are not separate facts. Together, they describe a world. And the world is immense. The deep ocean is the largest habitat on Earth by volume. Most of its living space is not reef or trench or vent, but open water and wide seafloor where animals may be scattered thinly through darkness. Human imagination often prefers concentrated scenes because cameras do. A vent field crowded with tube worms is easier to remember than kilometers of water where a small fish appears once and is gone. But the sparse world is not less real. It may be the more typical deep sea, and it is harder to understand because its scale overwhelms the frame. Scale changes the meaning of absence. On land, if you walk through a forest and see no deer, you do not conclude that deer do not live there. In the deep sea, a camera may travel for an hour through water or across sediment and see only a few animals, but the sampled volume is tiny compared with the habitat. Many animals are small, transparent, buried, distant, or outside the light. Others may avoid the vehicle. The apparent emptiness of a frame must be interpreted with sampling effort in mind. The deep ocean can look empty because our window is small. At the same time, some deep sea habitats truly are low density compared with shallow ecosystems. This is not failure. It reflects energy. Sunlit reefs and coastal waters receive direct photosynthesis or rich nutrient inputs. Abyssal plains often receive leftovers. Biomass is lower because food supply is lower. Animals adapt by needing less, moving less, growing slowly, or using rare pulses efficiently. To describe this world accurately, it must be allowed to be both sparse and alive, both difficult and functional, both less crowded in a camera beam and enormous across the planet. This balance is visible in the way an abyssal bait fall transforms a scene. Before bait, the frame may show sediment and a few tracks. After bait, amphipods arrive, then fish, then larger scavengers if the region supports them. The animals were not absent. They were dispersed, waiting, following chemical cues through water. Food creates a temporary center. The pressure world gathers around it. Then the food is gone, and the gathering dissolves back into darkness. Abundance in the deep sea is often temporary, local, and intensely used. A carcass can also reveal hierarchy. Small scavengers arrive quickly and feed in numbers. Larger fish may push through them. Crabs tear pieces away. Hagfish knot themselves for leverage. Bacteria work invisibly. If the carcass is large enough, the sediment around it changes chemically. If bones remain, a later community develops. The deep sea does not waste death, but neither does it romanticize it. Death is a resource, and where resources are rare, the response can be immediate and crowded. The pressure above does not make the process solemn. It makes it cold, dark, and efficient. The surface rarely sees this. A whale floating dead may become a news image, a navigational hazard, a smell near a beach. If it sinks offshore, it becomes something else entirely. The body passes below the depth of ordinary vision, below the reach of casual witness, and joins the deep food web. Most whale falls are never found by humans. Most deep carcasses are never filmed. The ocean does not need observation to complete the cycle. We discover some of these events and give them names, but the process existed long before any ROV light crossed a bone. Pressure also influences how remains preserve or disappear. Calcium carbonate can dissolve more readily below certain depths depending on temperature, pressure, and chemistry. Shells may dissolve before burial. Bones may be bored by worms and microbes. Soft tissue may be eaten quickly or slowly depending on temperature and scavenger access. A deep-sea fossil record is therefore selective. Many lives leave no recognizable trace. This is another reason the living deep sea must be studied directly. Rocks and jars preserve fragments, but the ongoing system is larger than what preservation favors. Even metals behave as temporary visitors. Shipwrecks in deep water may be preserved by cold and low oxygen, but they are still altered by corrosion, microbes, currents, and sediment. Cables laid across the seafloor become hard substrate for some organisms and obstacles or structures for others. Scientific instruments left for years return encrusted, stained, colonized, or sometimes lost. The deep sea is not a museum case. It is a chemical and biological environment. It changes what enters it, whether that object is a whale, a steel frame, a plastic bottle, or a titanium lander. There is a strange humility in seeing a machine colonized. A carefully machined surface, lowered with serial numbers and calibration records, becomes a place for microbes, hydroids, small worms, or sediment films. The object was built for human purpose, but the ocean assigns it additional roles. It becomes shade, structure, obstacle, substrate. The pressure world does not know the difference between equipment and habitat except through material, shape, chemistry, and time. If something remains, life may test it. But not all objects are harmless when they remain. Lost fishing gear can keep catching. Heavy equipment can crush. Mining collectors can raise sediment plumes. Noise can travel. Artificial light can change behavior. The fact that life colonizes an object does not absolve the object. Deep-sea ecosystems are opportunistic because opportunity is valuable, but they are also shaped by conditions that may not recover quickly from repeated disturbance. A pressure world can absorb some intrusions and be altered by others. The difference is empirical, not something we should guess casually. That is why baseline studies matter. Before disturbance, scientists need to know what is there, how it varies naturally, how species are distributed, how sediment functions, how currents move, and how often food arrives. Without that, damage can be mistaken for natural emptiness. If a place is poorly known before extraction, its losses may be invisible to anyone who was not looking carefully. The deep sea has often suffered from this problem. Because it is hard to see, people assume there is little to lose. The camera has repeatedly shown that assumption to be wrong. The camera also shows that value is not always dramatic. A small sponge attached to a nodule, a worm track in mud, a cluster of eggs, a brittle star on coral, a fish resting beside a rock. These are not spectacular in the way a black smoker is spectacular, but they are parts of functioning habitats. The deep sea is not made only of famous extremes. Much of it is ordinary within its own rules, and ordinary life is still life. Pressure worlds are not worth attention only when they threaten metal or reveal creatures that look impossible. They are worth attention because they are real. Real worlds have histories. The abyssal plain beneath NOAA may have received particles from blooms years earlier, ash from eruptions, dust from continents, microplastics from cities, and the remains of animals that lived and died above it. A vent field may have opened after tectonic movement and will one day fade. A trench may collect material from slopes and earthquakes. A cold seep may build carbonate over long periods. A whale fall may pass through stages and disappear into sediment. The deep sea is not timeless. It is time-rich, with histories recorded in chemistry, growth, and layers. This is one reason the phrase pressure worlds is useful. It suggests not just depth, but a set of conditions that produce different versions of reality. In one pressure world, animals migrate through dim light each night. In another, a vent chimney builds from minerals carried by superheated fluid. In another, a brine pool forms a shoreline beneath the sea. In another, a trench wall drops into water under more than 1,000 atmospheres. In another, a whale skeleton becomes a reef of bone. These worlds share pressure, but they are not interchangeable. The animals are not interchangeable either. Lanternfish are not snailfish. Tube worms are not sea cucumbers. Amphipods at a trenchbait fall are not the whole hadal ecosystem. A giant isopod is not a representative of all deep-sea scavengers. The vampire squid is neither squid nor octopus in the ordinary sense, and it does not spend its life attacking large prey. The Dumbo octopus is not a toy-like symbol of cuteness, but a deep-sea cephalopod moving through cold water with fins and webbed arms. Accurate attention means letting each animal be specific. Specificity makes the deep sea more interesting, not less. A tripod fish resting on elongated fin rays is stranger when you understand that it is positioning itself in current to intercept prey without wasting energy. A barrel-eye fish is stranger when you understand that its tubular eyes are adapted for detecting faint silhouettes above it. A loose jaw is stranger when you understand that some species use red bioluminescence that many other animals may not see well. A siphonophore is stranger when you understand it as a colony of specialized units rather than a single simple jelly. Some details remain uncertain. Behavior inferred from anatomy may be revised when footage appears. Depth ranges may expand. Diets may prove broader than expected. Genetic work may divide a species into several. New pressure experiments may change ideas about biochemical limits. The deep sea is full of provisional knowledge, but provisional does not mean worthless. It means honest. A careful statement can hold both evidence and uncertainty without turning the animal into a myth. Myth has always gathered around the deep ocean because humans see so little of it. Sea monsters, bottomless pits, giant unseen predators, black water without rules. Some of these stories began from real encounters: a stranded squid, a whale scar, a strange carcass, a net filled with damaged animals. But the real deep sea is more demanding than myth. It does not exist only to frighten the surface. It has food webs, larvae, microbes, pressure gradients, chemical boundaries, and animals whose lives are mostly ordinary to themselves. Reality is less simple than fear, and more interesting. The title says metal would collapse, and that is true in the right conditions for the wrong design. But the deeper truth is that collapse depends on mismatch. A hollow object from the surface collapses because it does not belong to the pressure around it. A human body collapses because its air spaces and physiology are not compatible with sudden deep pressure. A shallow animal may fail because its cellular machinery is tuned for another range. A deep animal may fail at the surface for the same reason in reverse. The ocean is not universally hostile. It is selective. Selection works without intention. Over generations, bodies that function at certain depths leave more descendants there. Bodies that cannot function do not. The result can look purposeful: soft tissues, pressure-tolerant proteins, altered membranes, reduced gas spaces, slow metabolism, large mouths, bioluminescent organs, sensory adaptations. But evolution did not plan a pressure world. It filtered variation through pressure, darkness, food scarcity, temperature, oxygen, predation, and chance. What remains is not perfection. It is adequacy refined by survival. Adequacy is easy to underestimate. A sea cucumber crossing the abyss does not look like a triumph, but it is one lineage's answer to a difficult planet. A vent mussel holding bacteria in its tissues is another. A brine pool mussel at the edge of toxic water is another. A snailfish moving under trench pressure is another. A jelly drifting in black water is another. Each is adequate to conditions that would destroy our machines unless those machines were built with extraordinary care. Life here is not invulnerable. It is matched. The match becomes more astonishing when you remember how narrow human access is. A dive to 6,000 meters may give researchers hours on the bottom after years of design, planning, funding, weather windows, ship time, permits, maintenance, and risk management. The animals are already there before the lights arrive and remain after the vehicle ascends. We enter with cost and return with samples. They remain with bodies. A pressure world is not defined by our ability to reach it. It is defined by the life and processes that continue when we leave. The same pressure that challenges exploration has also protected some habitats from casual disturbance for most of human history. But protection by inaccessibility is temporary. Better cables, robots, sensors, submersibles, and autonomous vehicles are expanding access. That expansion can support conservation if it produces knowledge before exploitation. It can support exploitation if knowledge is treated only as a way to reduce uncertainty for extraction. The technology itself is not moral. It is a tool. The choices around it determine whether pressure worlds are studied carefully or treated as remote storage for resources. This choice is becoming more urgent because the deep sea is increasingly discussed in terms of metals. Cobalt, nickel, manganese, copper, rare earth elements, polymetallic nodules, crusts, sulfides. The language of the future often reaches downward, toward batteries and infrastructure and energy transitions. But the title can be reversed. These are not only pressure worlds where metal would collapse, they are also living worlds where metal is being sought. The same seafloor that appears as mineral inventory to one map may appear as home, substrate, feeding ground, nursery, or unknown habitat to another. A responsible view has to hold both realities without pretending the decision is simple. Modern societies use metals. Energy systems require materials. But the deep sea is not an empty warehouse placed conveniently beyond sight. It is a set of ecosystems about which knowledge is still incomplete. And the incompleteness matters because harm can be easier to cause than to measure. Before wide-scale disturbance, the burden of evidence should be serious, not because the deep sea is mystical, but because it is slow, connected, and difficult to repair. Somewhere on an abyssal plain, a sponge grows from a nodule no wider than a human hand. Around it, sediment stretches farther than the lights can reach. Particles fall. A small animal passes. The nodule formed slowly, layer by layer, long before anyone wanted it. To remove it is easy only in the imagination. In the real world, removal means tracks, plumes, lost substrate, changed sediment, and a before and after that may outlast the machine. The pressure did not protect that sponge from being seen. It may not protect it from being taken. The same careful thinking applies to vents, although the mining target is different. Seafloor massive sulfides form around hydrothermal systems, rich in metals precipitated from vent fluids. Active vents support dense biological communities tied to chemical energy. Inactive deposits may also host life, sometimes less obvious and less studied. Disturbing these systems can affect not only the mineral surface, but the surrounding habitat, water chemistry, microbial communities, and species with limited distributions. The presence of metal is part of why the habitat exists. It is also part of why the habitat attracts human interest. A black smoker does not care about the economic value of its chimney. It is a geological and chemical structure, built by seawater circulating through crust and returning changed. The animals around it care only in the sense that their lives depend on the gradients it creates. If the flow stops, the community changes. If the structure is removed, the community changes. If sediment buries it, the community changes. Pressure is constant, but habitat is not. The deep sea has natural disturbance, and that fact is sometimes used to minimize concern. But natural disturbance is not a blank check for human disturbance. Scale, frequency, and recovery all matter. The more closely you look, the less the deep sea resembles a single backdrop for human ambition. It becomes a collection of places where life has negotiated with pressure in different ways. A glass sponge filtering slow water. A cusk eel nosing along sediment. A squat lobster on a vent chimney. A mussel full of symbiotic bacteria. A translucent sea cucumber lifting from mud. A fish with bones light enough to seem unfinished. A worm dissolving bone from the inside. These are not decorations on the edge of physics. They are the reason the physics matters. It is worth returning to the ROV, because the machine is where the human and animal pressure worlds meet. The pilots do not see the entire vehicle. They see camera angles, sonar, navigation, manipulator positions, depth, altitude, current, cable tension. Scientists call out observations. Someone records timestamps. Someone notes temperature or oxygen. The ship moves above, correcting position against wind and swell. Between the ship and seafloor hangs a long cable carrying power, commands, and images. The whole operation exists to create a narrow, temporary bridge between atmospheric life and deep pressure life. The bridge is fragile. Weather can end a dive. A thruster can fail. A connector can leak. A manipulator can jam. A sample can be lost during ascent. The tether can snag. Visibility can collapse in sediment. A planned transect can be abandoned because the bottom is rougher than expected. These practical details are not separate from science. They shape what can be observed. They decide whether a coral is sampled, whether a vent is reached, whether a trench-lander returns, whether a dataset is complete. The deep sea is difficult, partly because the pathway to knowledge is mechanical. And because it is mechanical, it has blind spots. Cameras favor animals large enough to see and close enough to illuminate. Nets favor animals durable enough to survive capture. Acoustics favor organisms or layers that scatter sound. DNA favors traces that persist and can be matched to reference libraries. Chemistry favors processes that leave measurable signals. No tool sees everything. A pressure world must be approached through a combination of methods, and the resulting picture will always have missing pieces. The honest narrator does not fill those pieces with certainty. The honest narrator leaves space for the next descent. There is a beauty in that restraint. The deep sea does not need exaggeration. A pressure housing descending into black water is already enough. A fish living where an unprotected human body cannot is already enough. A vent fluid held liquid above surface, boiling temperatures because of pressure, is already enough. A brine shoreline beneath the sea is already enough. A whale skeleton feeding worms in darkness is already enough. The real facts do not need to be made larger than they are. They need to be placed in the right light, and then allowed to remain real. The right light is often artificial. LED arrays mounted on an ROV. A lander flash. A submersible beam crossing sediment. A camera on a drop frame, firing in intervals. This artificial light creates the images by which the surface learns the deep sea, but it also changes the scene. Animals may freeze, flee, approach, or ignore it. Bioluminescent signals may be overwhelmed. Colors become visible that would not normally be visible. The footage is both revelation and disturbance. It shows the hidden ocean by briefly making it unlike itself. That limitation does not make the footage false. All observation has conditions. A microscope changes scale. A telescope gathers light that the eye cannot. A pressure chamber isolates variables. A sonar translates sound into structure. And ROV light creates visibility in a place without sunlight. The important thing is to remember the conditions and interpret accordingly. A deep-sea animal seen in white light is not necessarily experiencing its world as the camera shows it. Its own sensory world may be chemical, tactile, acoustic, pressure-sensitive, or tuned to faint flashes rather than continuous illumination. Many animals sense the deep sea through water movement. A fish's lateral line detects vibration and flow. A crustacean's antennae sample chemicals and touch. A predator may follow odor from a carcass. A vent animal may respond to temperature and chemical gradients. In darkness, the environment is not blank. It is textured by pressure, current, scent, sound, turbulence, particles, and living signals. Humans arrive with vision as the favored sense, then build machines to extend vision. But the animals may be reading a different version of the same place. Imagine the ROV from the animal's side, not as a heroic explorer, but as a sudden bright object with thruster noise, disturbed water, and chemical traces from materials that do not belong there. It hovers, turns, shines, reaches with a metal arm, and leaves. The animal's world returns to darkness after the disturbance passes. For humans, the dive may be the central event of the day. For the animal, it may be a brief interruption, if it registers at all. This reversal keeps the story grounded. We are not the center of the pressure world. We are visitors. Visitors must carry their own survival with them. The human body is full of pressure-sensitive spaces, lungs, sinuses, ears, gases dissolved in blood and tissues. Diving medicine exists because changing pressure too quickly can injure or kill. Submersibles avoid this by keeping people at surface pressure inside a hull, but that turns the hull into the critical boundary. If the boundary fails, the body has no adaptation for the outside. The deep ocean is not dangerous because it is angry. It is dangerous because our physiology belongs to a narrow band near the top of the water column. Even ordinary scuba divers encounter pressure quickly. At 10 meters, pressure is about 2 atmospheres. At 30 meters, about 4. Technical divers plan gas mixtures, decompression, narcosis, oxygen toxicity, and ascent schedules. But the deep sea discussed here begins far below the range of ordinary diving. At 1,000 meters, no diver is going outside a vehicle. At 4,000 meters, the world belongs to robots, submersibles, and animals. At 11,000 meters, even the machines are rare. Depth turns human access from athletic problem to engineering problem. Engineering success can create another illusion, that because a machine can go there, the place has been mastered. But reaching depth is only one capability. Staying there, sampling gently, navigating complex terrain, preserving pressure, measuring chemistry, observing behavior without overwhelming it, and returning repeatedly are different capabilities. The deep sea is not conquered by a single descent any more than a continent is understood by stepping once onto a beach. Each successful dive expands reach, but the world remains larger than the mission. Some dives find exactly what they set out to find. Others find a slope where the map promised flat ground, a current stronger than expected, a vent that has gone quiet, a field of animals no one anticipated, or nothing obvious at all. Nothing obvious is still information if recorded carefully. Absence can shape hypotheses. Sediment type, temperature, oxygen, and current can explain why a place has fewer animals than another. The pressure world does not owe every dive a spectacle. Sometimes it offers context, and context is what turns rare moments into understanding. A quiet dive over sediment may reveal feeding traces arranged like handwriting, small furrows where animals plowed through the surface, paired marks from fins, holes surrounded by little mounds, a line where a sea cucumber passed. These marks are behavior preserved briefly in mud. They show that animals were present before the camera arrived. They may tell scientists about movement, feeding, population density, and sediment mixing. In a world where direct observation is brief, traces become important witnesses. Trace evidence appears in other forms too. Sucker scars on whales, squid beaks in stomachs, bite marks on carcasses, mineral crusts around seeps, shell accumulations near vents, na in water, chemical anomalies in sediment, acoustic scattering layers. Each trace is incomplete. Together, they can reveal relationships that no single camera would catch. Deep sea science often feels like reconstructing a large, slow-moving event from fragments left in darkness. The fragments are not poetic by themselves. They are useful because they can be tested against each other. The pressure world also leaves traces on the animals after death. A deep fish hauled upward may show barotrauma, organs displaced by expanding gas, eyes damaged, stomach everted. A gelatinous animal may become unrecognizable. A crustacean may survive better because its exoskeleton holds form, but its behavior is gone. These altered bodies once fueled myths of monsters because they looked wrong on deck. In reality, the wrongness often belonged to the removal. The body had been taken out of its pressure, and the surface misread the result. Seeing living footage corrects that misreading. The deep sea fish with a huge mouth is not always gaping. The jelly is not a shapeless blob. The squid is not a torn mass of arms. The sea cucumber is not a sack, but a moving animal with direction. The anglerfish is not a theatrical villain, but a body suspended in a dark economy. The living deep sea is often quieter, more controlled, and more functional than its dead surface images suggested. Function can be beautiful without becoming decorative. A siphonophore stretching through the water may be longer than a whale and more delicate than a ribbon. It is not one animal in the ordinary sense, but a colony of specialized units, some for swimming, some for feeding, some for reproduction. Its shape may be almost impossible to preserve. A net would break it. A jar would compress its meaning. Only in the water does it become legible. Pressure does not crush it because it is not fighting pressure with hollowness. It is a living architecture made mostly of water. Gelatinous animals are often undercounted by traditional sampling because they are fragile. This matters because they may be ecologically important as predators, prey, and carbon transporters. Salps, jellyfish, ctenophores, siphonophores, and other soft-bodied organisms can dominate certain midwater scenes. Some produce fast-sinking fecal pellets or carcasses that carry carbon downward. Some feed on small crustaceans or fish larvae. Some are eaten by turtles, fish, or other gelatinous predators. The pressure world contains many animals that look insubstantial to us but function as substantial parts of food webs. Their fragility also challenges the language of strength. A ctenophore can be destroyed by a rough jar, but remain perfectly suited to pressure, cold, and darkness. A metal housing can survive a launch crane and rough handling, but fail under compression if shaped badly. Strength is always contextual. It depends on what kind of force is applied and what function must continue afterward. The deep sea makes this obvious by placing fragile-looking bodies in conditions that break robust-looking objects. The camera drifts past another animal, and for a moment, the title feels less like a threat than a question. What does collapse mean here? The metal frame survives because engineers anticipated the pressure. The animal survives because its lineage belongs to it. The only thing that collapses quickly is the assumption that surface ideas of strength are universal. The deep sea is not upside down. It is simply built on different premises. Those premises become clearest at the boundary between air and water. A ship floats because its hull encloses air and displaces water. A submarine dives because buoyancy is controlled. A deep submersible descends because ballast, foam, and pressure hull are balanced carefully. But if that hollow structure is taken below its design limit, the same air that made it buoyant becomes part of its vulnerability. The ocean is strongest against emptiness. Life in the deep sea avoids emptiness wherever possible. Some animals do use gas spaces, especially at shallower depths and in migrating layers, but deep life often reduces or modifies them. Swim bladders may be absent, lipid-based buoyancy may be important, or gas may be tightly regulated. Marine mammals carry air but collapse parts of their lungs and manage gases during dives in ways that reduce injury. Different lineages have different relationships with compressible spaces. The pattern is not a simple rule that gas is impossible. It is that gas under changing pressure must be managed, and the cost of managing it grows with depth and movement. A lanternfish rising at night is therefore not only moving toward food. It is crossing pressure, temperature, light, and predator fields. Its body must handle the change. Its timing must match darkness. Its predators may follow. Its prey may be above. When dawn approaches, it descends again, joining a layer that sonar may detect as a shifting band. This migration is one of the largest daily movements of biomass on Earth, and it happens mostly without human witness. The pressure world is not still. Every night, part of it moves upward and then returns. That movement connects the surface and deep water in a living way. Animals feed near the surface and excrete at depth. They carry carbon downward in their bodies. Some are eaten during migration, transferring energy to predators. Some die and sink. Marine snow is not only passive fall, it is also produced, transformed, and transported by animals moving through the water column. The pressure gradient becomes part of a daily biological pump, a rhythm tying sunlight to darkness through the bodies of small fish and invertebrates. This biological pump matters for Earth's carbon cycle. Not every particle that leaves the surface reaches the abyss. Much is consumed or decomposed in the upper and middle depths, but the fraction that sinks deeper can keep carbon away from the atmosphere for long periods. The deep sea is therefore part of the climate system, not just a remote habitat. Its animals, microbes, and particles influence how carbon moves through the ocean. A pressure world can be hidden from human eyes and still participate in planetary regulation. This makes disturbances harder to evaluate. Changing surface productivity changes food supply below. Removing midwater biomass could affect carbon transport and predators. Disturbing sediments could alter carbon storage and microbial processes. Mining nodules could affect habitats and plumes. Fishing slopes can damage long-lived communities. The deep sea is connected upward to climate and downward to geology, and human impacts can travel through those connections. The fact that many processes are slow does not make them unimportant. Slow systems can be fundamental. Pressure testing a deep sea housing can look uneventful from outside the chamber. A metal cylinder or glass sphere is placed inside, the door is closed, and pumps increase the load until the gauge reaches the required level. There is no darkness, no animals, no drifting snow, no canyon wall moving through a camera beam. There is only a laboratory version of depth. Yet this quiet test may decide whether a future dive sees the seafloor or goes blind. If the housing holds, it becomes trusted. If it fails, the failure happens safely in a place designed to contain it, not thousands of meters below a ship where recovery may be impossible. The shape of the test object matters as much as the material. A thick piece of metal can be made weak by geometry. A thinner piece can survive if the load is distributed properly. This is why the deep sea favors curves for anything that must remain hollow. A sphere has no corner where stress gathers. A cylinder can work if the ends are designed carefully and the wall is thick enough. A cube is far less forgiving. It may look strong on a workbench because its faces are flat and its edges are sharp, but those same faces and edges become liabilities under even compression. The ocean does not admire the appearance of sturdiness. It calculates through force. Viewports are among the most psychologically important parts of a human-occupied submersible because they allow a person to look directly into the deep. They are also engineering problems. A viewport must be transparent, strong, precisely seated, and shaped so pressure helps seal it rather than pry it loose. The person inside may be watching a fish or a vent chimney, but the window between them and the water is under a load that would flatten ordinary glass. That small circle of visibility is not simply a window. It is a pressure boundary, and every view through it depends on mathematics, machining, inspection, and trust. The animals outside the viewport do not know they are being watched through a triumph of material science. A shrimp may cross the light. A fish may turn broadside and then vanish. A crab may lift one claw in the disturbed current. These movements are ordinary, but they occur beside a human being kept alive by a hull that has been built to exclude the very condition the animal requires. The scene is intimate and unequal. One body belongs there. The other is protected from belonging there. Some of the most revealing pressure stories are not about full ocean depth dives, but about small parts that fail at more moderate depths. A connector leaks because a seal was nicked. A cable jacket deforms. A buoyancy block compresses more than expected. A camera fogs because a tiny amount of moisture was trapped inside. A battery enclosure comes back with evidence of intrusion. These failures are less famous than spectacular implosions, but they teach the same lesson. The deep sea is not impressed by intent. It tests every component according to its own physical conditions. This is why redundancy matters. A deep vehicle may carry more than one camera, more than one light, more than one way to release weight, more than one navigation aid. Redundancy is a form of humility. It admits that the pressure world can defeat a part that was expected to work. It also admits that ship time is valuable and that a failed dive may represent not only a broken object, but lost observations, lost samples, lost weather windows, and lost chances to see a living system at a particular moment. Engineering in the deep sea is never separate from the biology it hopes to reveal. A manipulator arm is a good example. To a viewer, it may look like a mechanical hand reaching toward a rock or animal. To the engineers and pilots, it is a series of joints, seals, hydraulics, motors, sensors, and control delays, all functioning under pressure. It must be strong enough to lift a sample, gentle enough not to crush it, and precise enough to place a tool in current while the entire vehicle moves slightly. When it closes around a piece of coral or a vent rock, it is not simply grabbing. It is translating human curiosity into motion through a machine that the ocean is trying to compress. Sometimes the most important act is not touching. A pilot may hold the vehicle still and let the camera do the work. A coral too fragile to sample may be filmed, measured with lasers, and left standing. A fish may be followed for a short time and then allowed to leave the beam. A vent opening may be approached slowly to avoid stirring particles or overheating a sensor. The deep sea rewards restraint because every movement costs something: battery power, time, visibility, or contact with a habitat that may not recover quickly from careless disturbance. Scaling pressure from a small instrument to a large vehicle is not straightforward. A small sphere can be made thick relative to its size. A large human sphere requires more material, more exact manufacturing, and more careful testing. A small flaw that would be insignificant in a shallow water housing can become serious when the stored energy of compression is large. This is one reason deep ocean vehicles often look compact around the human compartment. People may want space, but space means volume, and volume enclosed at one atmosphere creates a larger boundary for the ocean to press against. The animals avoid that problem by not carrying rooms. Even a large squid is not a hollow chamber. A whale that dives deep carries air, but its body manages that air through collapsible lungs, blood chemistry, muscle oxygen stores, and dive responses that reduce problems from pressure changes. It does not descend as a rigid tank. It descends as a mammal adapted for repeated compression and return. The comparison is useful because it shows that biology does not have one strategy for pressure. A jelly, a fish, a squid, and a whale meet pressure differently because their bodies and life histories require different compromises. Marine mammals are not deep-sea residents in the same sense as trenchfish or abyssal worms, but they are important visitors to pressure worlds. Sperm whales, beaked whales, elephant seals, and some other divers enter depths where darkness and pressure are significant. They do so while remaining tied to the surface for air. Their lives connect surface breathing to deep feeding, and their bodies carry adaptations for oxygen storage, pressure changes, and long dives. They also carry evidence back upward in stomach contents, scars, tags, and behavior recorded by instruments attached to their bodies. A tag on a diving animal is a small passenger through pressure. It records depth, time, acceleration, sometimes sound, sometimes temperature, and then detaches or transmits data. From that data, scientists can reconstruct dive profiles that no camera followed. A whale descends, levels out, changes movement, perhaps hunts, then rises. An elephant seal crosses thousands of meters of vertical water over and over during a foraging trip. These records show that pressure worlds are not sealed below us. They are visited by air-breathing predators that know them through sound, body memory, prey fields, and repeated descent. But even these powerful divers have limits. They cannot remain indefinitely. They must manage oxygen debt, pressure changes, and the need to breathe. A deep squid or fish does not have to return to the surface after each feeding event. A vent worm does not ascend. A hadal amphipod does not commute to sunlight. There is a difference between visiting a pressure world and being born into one. Visitors may be impressive, but residents reveal the deeper adaptation. Residency can be quiet. A bristlemouth in the midwater may be one of the most numerous vertebrates on Earth, yet most people will never see one alive. It is small, dark, and easily overlooked beside the more dramatic images of anglerfish and giant squid. Its abundance matters more than its fame. In the dim layers of the ocean, small fishes and crustaceans form the living fabric that supports larger predators and transfers energy through the water column. A pressure world is held together not only by rare spectacles, but by common animals performing common acts on an immense scale. Bristlemouths, lanternfish, and other mesopelagic fishes often have photophores arranged in species-specific patterns. These lights can help with camouflage, signaling, or recognition. In a place where faint light still comes from above, producing light from below can erase a silhouette. This is counterillumination, and it is one of the more elegant examples of deep-sea adaptation because it uses light to create darkness. The fish does not become invisible in every direction. It reduces detection from below, where a predator looking upward might otherwise see its outline against the remaining glow. Counterillumination depends on matching the light field, and the light field changes with depth, time, cloud cover, water clarity, and moonlight. This means the behavior and physiology behind it must be adjustable. Too bright, and the animal becomes a signal. Too dim, and the silhouette remains. The solution is not simply having lights, it is controlling them. In the deep ocean, bioluminescence is often described as beautiful, but to the animal, it is useful only if it is regulated. The same is true of lures. A glowing lure that attracts prey may also attract predators or competitors. A flash meant for communication may reveal position. A defensive burst may startle one animal and alert another. Light is not free. It has chemical cost and ecological risk. The deep sea uses light because sunlight is absent or diminished, but that absence does not make every glow advantageous. Each glow must fit a context, and the context includes pressure only as the setting in which the signal travels. Some dragonfish carry this light strategy further by producing or detecting wavelengths that many deep animals may not perceive well. Their jaws are armed with long teeth, their bodies dark, their photophores precise. They look severe in photographs, but their severity is not theatrical. It is a predatory design for midwater. They move through a three-dimensional darkness where prey may be seen only briefly, and where body outline, light control, and sensory range affect whether a hunt succeeds. The pressure around them is high by human standards, but the real drama of their lives may be detection distance and energy balance. Energy balance appears again in the vampire squid. Its name suggests violence, but the animal itself often feeds on detritus, collecting marine snow and small particles with long filaments. It lives in oxygen-poor water, where many active predators would struggle. It can turn its webbed arms over its body, release bioluminescent mucus, and move with economy. The name belongs to human imagination. The body belongs to a low-oxygen, low-food, dark midwater world, where survival may depend more on patience and efficiency than on attack. Oxygen minimum zones create habitats that are not simply deeper versions of normal water. They can exclude some predators, compress migrations, and favor animals with low oxygen demands or specialized physiology. In these layers, pressure may be moderate compared with trenches, but the combination of low oxygen and dim light creates its own constraints. A species able to tolerate that water gains refuge from animals that cannot. Another species may be forced above or below it. The water column becomes structured by invisible chemical boundaries, as real as a reef wall or a canyon edge. Invisible boundaries are difficult for viewers because the camera does not show them directly. The beam illuminates particles and animals, but not oxygen concentration, pH, pressure, or dissolved methane. Instruments translate those conditions into numbers. The narration has to do the rest, making clear that the scene is more than what the eye receives. A fish hovering in apparently empty water may be positioned at a boundary that matters deeply to its body. A mussel bed may mark seepage invisible except through chemistry. A lack of animals may mark water too poor in oxygen for them to remain. The deep sea is therefore a place where measurement and image must be paired. The image alone can seduce with form. The measurement alone can become abstract. Together, they show habitat. A temperature spike beside a vent makes the shimmering water meaningful. A methane reading beside white mats explains why bacteria grow there. A depth reading beside a snailfish explains the pressure range in which its body works. An oxygen profile beside a migrating layer explains why animals gather where they do. Science turns the visible into the interpretable. The farther down the vehicle moves, the more the ship above becomes an idea rather than a place. The tether stretches through darkness. Acoustic signals travel upward. Pilots sit in chairs, but the machine they control is in a pressure world that no one in the room could enter directly. A sample arm moves after a command travels down. A camera pans across sediment that may lie 4 kilometers below the nearest breath of air. This delayed control creates a strange intimacy. The humans are far away, but their attention is precise. Precision is not always possible in strong current. A vehicle may drift. A manipulator may approach a sample from the wrong angle. Sediment can obscure the target. A fish may appear just as the pilot is trying to avoid a rock. Deep sea work often involves compromise in real time. The best plan made on deck meets the actual seafloor only during the dive. This is another reason long-form footage can feel slow. The slowness is not empty. It is caution under pressure, caution near fragile animals, and caution in a world where mistakes can be expensive. When mistakes happen, they may leave marks. Thruster scars in sediment. Broken coral. Lost equipment. A sample container closed too hard. A bait package that lands on an animal. Most scientific teams work to avoid this, but the possibility is part of the ethical reality of exploration. To know the deep sea, humans disturb it. The question becomes how much disturbance is justified by the knowledge gained, and whether that knowledge is used to protect the habitat or only to make further intrusion easier. The same question applies to images. Deep sea footage can inspire care, but it can also turn animals into content detached from habitat. A strange fish becomes a viral clip. A vent becomes a backdrop. A brine pool becomes a novelty. The responsibility of narration is to return the animal to its world. The fish has a depth, a pressure range, a prey field, and a body shaped by constraints. The vent has chemistry and microbes. The pool has density and toxicity. Without those anchors, the deep sea becomes a gallery of oddities instead of a living system. A living system includes things too small for the camera to celebrate. Microbes form the base of vent and seep food webs. They break down sinking organic matter. They transform nitrogen, sulfur, methane, and carbon compounds. They live in sediments, on rocks, in animal tissues, and in the water column. In many deep habitats, the most important work is invisible to the eye. A mussel bed is visible because microbes inside the mussels make it possible. A whalebone community depends partly on microbial chemistry. A sediment surface changes because microbial processes alter what larger animals can use. Microbial life also complicates the boundary between geology and biology. At vents, microbes use chemicals from the Earth's crust. At seeps, microbes use methane and sulfide from below the sediment. In whale falls, microbes transform bone and tissue into chemical energy that supports later communities. In sediments, microbes process the slow rain of organic matter. These processes connect rock, water, animal remains, and living bodies. The pressure world is not only a place where animals endure depth, it is a place where chemistry becomes food through microbial work. This microbial foundation raises a larger question about habitability. If life can thrive without sunlight at vents and seeps, powered by chemical energy. Then, the deep sea becomes relevant to thinking about life beyond Earth. Icy moons with subsurface oceans, rocky worlds with water and chemical gradients, places without sunlight but with energy sources become easier to imagine as habitats. The deep ocean is not an alien world, but it helps humans think more clearly about what alien habitability might require. Pressure, darkness, and chemistry are not automatically prohibitions. They are conditions. That comparison should be used with restraint. Earth's deep sea is connected to a surface biosphere, a breathable atmosphere, plate tectonics, and billions of years of evolution. A vent ecosystem here does not prove life elsewhere, but it does expand the range of environments where complex communities can exist. It shows that sunlight is not the only possible foundation for food webs. It shows that pressure and darkness can be compatible with life if chemistry, water, and adaptation align. The lesson is not certainty about other worlds. It is a broader understanding of this one. Understanding this world changes the meaning of the surface. The calm sea above a trench is not the opposite of the pressure world below. It is the top of it. The plankton blooming in sunlight may feed animals kilometers down. A storm may alter sinking particles. A whale breathing at the surface may one day feed worms on the bottom. A ship lowering a vehicle is not entering a separate planet, but moving through one continuous ocean whose conditions change with depth. The division between surface and deep is practical for humans, not absolute for the sea. Pressure makes that continuity dangerous for us. A line can pass through it. A signal can pass through it. Sound can pass through it. Sinking particles can pass through it. Animals can migrate through parts of it. But a human body cannot freely pass through it, and most of our objects cannot either. We live at the top of a pressure gradient we rarely think about because air is light compared with water. The deep ocean is not distant only horizontally, across miles from shore. It is distant vertically, through a column of weight that changes what bodies and materials can be. This vertical distance has shaped the history of ocean science. For a long time, the deep sea was sampled by ropes, dredges, thermometers, lead lines, and nets. Then came stronger cables, echo sounding, bathyspheres, submersibles, ROVs, AUVs, landers, satellites mapping sea surface height to infer seafloor shape, and increasingly sensitive chemical and genetic tools. Each technology opened a different window, and each window revealed that earlier assumptions were incomplete. The deep sea was not lifeless. It was not uniform. It was not disconnected from the rest of Earth. It was simply hard to reach. Even now, maps of the seafloor are uneven in resolution. Some areas have been surveyed in great detail. Others are known more broadly. A trench may be mapped after a major expedition. A seamount chain may remain poorly sampled biologically. A canyon near a coast may have more observations than a remote abyssal plain. Knowledge follows ships, funding, weather, politics, and scientific priorities. The ocean's hiddenness is not only a natural fact, it is also the result of where humans have chosen and been able to look. When a new map appears, it can change the next dive before the vehicle enters the water. A slope once thought smooth may reveal terraces. A plain may show pockmarks from seepage. A ridge may show possible vent sites. A canyon may show tributaries and collapsed scars. The map does not show the animals in detail, but it gives them possible addresses. Then, the ROV descends to see whether the geology and biology match expectation. Sometimes they do. Sometimes a map feature that looked promising is bare. Sometimes a modest feature holds an unexpected community. This uncertainty is not a failure of mapping. It is the difference between structure and life. Rock shape influences habitat, but it does not guarantee it. A vent requires heat and fluid flow, not just a ridge. A seep requires chemistry, not just a depression. A coral garden requires suitable substrate, current, larvae, and time. A trench slope may receive food differently depending on currents and earthquakes. The pressure world is not predictable from depth alone or shape alone. It emerges from overlapping conditions, some visible on maps, and some measurable only in place. In place, the world can be unexpectedly plain. A famous depth may look like mud. A record-setting trench may show sediment and small animals rather than grandeur. A biologically important seep may appear as pale mats and shells. The lack of visual drama can be misleading because importance is not always cinematic. A microbial process may matter more than a spectacular animal. A small boundary in chemistry may define an entire community. The pressure world often asks the viewer to care about evidence before spectacle. Caring about evidence is also a protection against fantasy. The deep sea is not a place where any imagined creature can be placed just because humans have not seen everything. It has constraints. Food supply limits body size and abundance. Pressure limits physiology. Temperature affects metabolism. Reproduction must work. Larvae must disperse or remain. Predators need prey. Prey need food. The unknown is large, but it is not lawless. Speculation becomes useful only when it respects the rules already known. This makes the real unknown more powerful, not a blank space for monsters, but a set of unanswered questions about living systems. How many species remain undescribed in abyssal sediments? How larvae find isolated vents? How deep sea animals respond to changing oxygen? How pressure adaptation evolved repeatedly? How whale falls are distributed across migration routes? How much carbon is stored or recycled at different depths? How communities recover after disturbance? These questions are quieter than legend, but they reach deeper because they can be answered. Answering them requires patience that matches the habitat. A single expedition can collect valuable data, but long-term observatories show change through time. Repeated transects reveal trends. Tagged animals reveal movement. Pressure experiments reveal mechanisms. Genetic surveys reveal hidden diversity. Sediment traps reveal seasonal pulses. Cameras left on the bottom reveal scavenger succession. The deep sea cannot be understood only by heroic descents. It needs sustained attention, the kind that returns after the exciting first image has already been shown. Sustained attention is difficult because deep sea work is expensive and logistically demanding. Ships burn fuel. Crews need training. Weather interrupts. Vehicles require maintenance. Permits in international waters complicate research. Samples must be processed. Data must be archived. Behind every clear image of a strange animal is a large human system of technicians, engineers, pilots, sailors, scientists, funders, and institutions. The pressure world appears on a screen as a quiet scene, but reaching that quiet scene is a collective effort. The collective effort also extends to naming. When a new species is described, the name attaches it to scientific language, but the animal existed before the name. It had predators, prey, larvae, genetics, and habitat before humans recognized it. Naming is not creation. It is admission into a system of knowledge. A named animal can be compared, protected, studied, and discussed more precisely. In a deep sea facing possible extraction and climate stress, naming can become more than taxonomy. It can become evidence that something specific is at stake, but many species may be affected before they are named. This is especially true for small invertebrates, microbes, and animals in undersampled regions. A nodule field may contain species known only from that field, or from a few samples nearby. A vent may hold lineages with limited dispersal. A trench may contain endemic fauna. If disturbance arrives before description, science may record loss only vaguely, as reduced abundance or altered community composition. The pressure world can lose details before those details have entered human language. There is a particular sadness in that possibility, because the deep sea's anonymity has often been mistaken for expendability. An unnamed worm, a small crustacean, a sponge on a nodule, a microbial mat on a seep, these do not easily compete with human needs in public imagination. But ecosystems are not built only from charismatic species. They are built from interactions. Remove enough small, unnamed parts, and the larger pattern changes. The deep sea does not become valuable only when a familiar animal appears in the frame. A frame full of sediment can still contain a community. The surface layer may hold bacteria, meiofauna, burrowing animals, chemical gradients, and organic particles being processed slowly. A sea cucumber track may expose deeper sediment. A worm may irrigate a burrow. A small crustacean may graze microbial films. These processes do not look dramatic at the scale of a YouTube thumbnail, but they are how the abyssal plane functions. The pressure world is often most itself when almost nothing seems to happen. This is why sediment plumes from disturbance raise concern. Fine particles can travel, settle, clog feeding structures, bury small animals, alter microbial processes, or change the surface layer through which many organisms feed and breathe. The severity depends on particle size, current, duration, chemistry, and habitat. It should not be assumed to be catastrophic everywhere, and it should not be assumed harmless either. The correct response is measurement before, during, and after disturbance, with enough time to see delayed effects. In the deep sea, delayed effects may be the most important ones. The deep ocean asks for a longer imagination than the surface usually demands. A coral may have begun growing before a city was founded. A nodule may have started forming before our species existed. A trench may collect sediment from events separated by centuries. A whale fall may host communities longer than a human childhood. A vent may flare and die on geological schedules, while its animals depend on larvae reaching the next active site. The pressure is immediate, but the histories are long. Long histories do not make the deep sea remote from the present. They make the present more consequential. A decision made in a few years can affect structures that formed over millions. A trawl passing once can break organisms older than the person steering the ship. A mine plan can target deposits built by slow chemistry and inhabited by species still being described. The mismatch between human decision time and deep sea formation time is one of the quiet tensions in the subject. It is not dramatic in the moment, but it is enormous in consequence. There is also a mismatch between the pressure that damages machines and the pressures of policy, industry, science, and public attention. Engineers ask whether a housing can survive depth. Biologists ask what lives there. Chemists ask how matter moves. Companies ask what can be extracted. Regulators ask what rules apply. The public may ask why a place no one visits should matter. The answer cannot rely only on mystery. It has to rely on evidence, biodiversity, carbon cycling, food webs, evolutionary history, vulnerability, and the simple fact that unknown does not mean empty. The deep sea should not be protected because it is beyond humanity. It is no longer beyond humanity. It should be treated carefully because it is part of the planet's living system, because our knowledge is incomplete, and because the conditions that make it hard to study also make damage hard to detect and repair. Pressure once served as a barrier. Technology is turning it into a challenge. What happens next depends less on whether metal can survive, and more on what humans decide to do once it can. For now, the camera still descends. The pressure still gathers. The control room still watches. A fish still appears where an unprotected machine would fail. A jelly still holds its shape in the dark. A vent still releases mineral-rich fluid into cold water. A mussel bed still farms bacteria in its tissues. A whalebone still feeds worms long after the whale's last breath. The facts are enough. They do not need to become legend. They only need to be followed carefully, downward, into the worlds where collapse and life exist side by side. One of the simplest demonstrations of pressure uses a foam cup lowered on a line. At the surface, the cup is ordinary, light, and full of trapped gas in the foam. At depth, The gas spaces compress, and the cup returns shrunken, its shape preserved in miniature. The demonstration is often used because it is easy to see, but it carries a deeper point. Many materials that seem solid to us contain spaces. Foam is mostly space. Some composites contain voids. Even metals may have flaws, inclusions, or weld defects. Pressure finds the spaces and makes them honest. The deep ocean also finds assumptions in language. People say the water is crushing, and it is, but crushing suggests a visible force pressing downward. The real force is hydrostatic and nearly equal from all directions at a point. This is why a well-made sphere survives better than a flat-sided box. It is also why a soft animal does not flatten like a footstep in mud. The pressure is not a hand pushing from above. It is an everywhere condition. The animal is under it, inside it, and balanced with it, while a hollow object from the surface carries an imbalance that must be engineered away. The pressure gradient begins shaping exploration before the vehicle even leaves the ship. Checklists include seals, vacuum tests, leak checks, battery status, ballast, camera ports, manipulator function, navigation beacons, and emergency recovery systems. These steps may seem procedural, but each is a response to a world that cannot be repaired casually once the vehicle is gone. A missing O-ring, an improperly tightened connector, or a scratched sealing surface can matter more than the grand design. Deep-sea exploration depends on large ideas and very small pieces of rubber. On the animal side, the small pieces are molecules. A membrane is not a wall like a hull, but it must keep the cell's interior organized. Under cold and pressure, membranes can become less fluid unless their lipid composition changes. Proteins must fold into shapes that allow reactions to happen. Enzymes must remain flexible enough to work. Nerves must transmit signals. Muscles must contract. These processes are ordinary life processes, but in the deep sea they occur under conditions that would change their behavior in shallow organisms. Adaptation is not always visible because much of it is chemical. This hidden chemistry can make deep animals difficult to keep alive in aquariums. It is not enough to provide salt water and food. Temperature, pressure, oxygen, light, flow, and sometimes diet or microbial partners must be appropriate. Many deep-sea species cannot be displayed easily because the conditions that make them normal are hard to reproduce. Even when pressure is not fully replicated, cold and darkness may be required. A deep-sea animal in a public exhibit is therefore not just an animal in a tank. It is the result of a life support system trying to imitate a world far below the building. The attempt to recreate deep conditions reveals how integrated those conditions are. Chilled water must be stable. Lights must be dim or controlled. Food must suit animals that may feed differently from shallow relatives. Flow must carry particles without blasting delicate bodies. Tanks must prevent injury from surfaces that animals would not encounter in open water. If pressure is included, the engineering becomes even more demanding. The challenge is not simply keeping an animal alive. It is keeping enough of its world around it that its body can continue to behave like itself. Some deep-sea animals survive surface pressure better than others. Crustaceans with stronger exoskeletons may remain recognizable. Certain fishes may be kept if brought up carefully from moderate depths. Many gelatinous animals require specialized collection chambers to avoid damage. Microbes from vents or sediments may need pressure and chemistry maintained to show their natural activity. The variety of responses reminds us that deep sea life is not one category of toughness. It is many lineages with different tolerances, and those tolerances cannot be guessed from appearance alone. A delicate comb jelly may require more careful handling than a rock from a vent, but the rock may carry microbes and chemical gradients that are also easy to alter. A sea cucumber may look robust and still depend on sediment conditions that are destroyed when it is lifted away. A mussel from a seep may carry symbionts that need chemical substrates no ordinary tank provides. The deep sea teaches that context is part of the organism. Remove the context too completely, and the body remains while the life it represented becomes harder to understand. Context includes sound. The deep ocean is dark, but it is not silent. Earthquakes, whales, rain at the surface, breaking waves, ship engines, seismic surveys, ice movement, and animal sounds can travel through water. Some of these sounds are natural parts of marine life. Others are industrial additions. Sound can move farther than light, and in a world where vision is limited, acoustic disturbance may matter in ways that are difficult to measure. Pressure does not block sound from relevance. It gives sound a medium. We should be cautious here because the effects of sound vary by species, frequency, intensity, duration, and context. A whale is not a shrimp. A fish with a swim bladder may respond differently from an animal without one. A brief sound may matter less than chronic noise. Some animals may move away. Others may show stress or altered behavior. Much remains under study. But the deep sea should not be imagined as protected from noise simply because it is dark and far below the surface. Human activity can enter pressure worlds as vibration as well as objects. The camera does not show vibration easily. It shows the animal and the light. It does not show the ship's engine transmitted through the hull, the thruster noise of the ROV, the acoustic positioning signals, or the distant soundscape of the ocean. A fish leaving the frame may be responding to light, pressure waves, electrical cues, scent, or the movement of water from the vehicle. Observation always arrives with a presence larger than the image suggests. The frame is visual, but the encounter is multisensory. Electric and magnetic cues may also matter to some animals, especially fishes and invertebrates able to detect weak fields or chemical gradients. Subsea cables, metal structures, and powered vehicles can introduce signals not normally present in a habitat. The significance depends on the species and setting, and it should not be exaggerated without evidence. But it is another reminder that entering the deep sea is not simply a matter of placing a camera in darkness. Machines carry materials, heat, light, sound, motion, chemistry, and fields. The pressure world receives all of them. The more dimensions we add, the less convincing the old image of the deep sea as empty black water becomes. It is black to human eyes without lights, but it is textured by cues that animals use. It is empty only if abundance is judged by a shallow reef standard. It is hostile only if judged by surface physiology. It is remote only from a human starting point. From the perspective of a larva drifting between vent fields, or a fish following the edge of an oxygen layer, it is a navigable world with gradients, signals, risks, and opportunities. Larvae are among the least visible travelers in these pressure worlds. A vent adult may be fixed to rock, but its offspring can enter the water column and disperse. Some larvae may delay development, ride currents, respond to chemical cues, or settle when conditions are suitable. How they locate rare habitats in a vast ocean is one of the central questions of deep-sea ecology. The adult community may look stationary, but its future depends on movement at a scale the camera rarely captures. The next generation begins as something almost invisible, searching for a place it cannot understand in any human sense. The idea of searching without understanding is not unique to larvae. A scavenger following odor from a carcass is not thinking about ecology. It is moving along a chemical path. A fish holding in current is not thinking about hydrodynamics. It is maintaining position where prey may pass. A tube worm does not know chemosynthesis as a concept. Its symbionts convert chemicals into food. The pressure world is full of processes that can be described scientifically but are lived without concepts. This is part of the humility of biology. Explanation belongs to observers. Function belongs to organisms. Currents are another form of structure. They deliver food, oxygen, larvae, and chemical signals. Around seamounts and ridges, currents may accelerate or form eddies. Along slopes, they may carry particles or resuspend sediment. Near vents, Buoyant plumes rise and mix with surrounding water. In trenches, currents and downslope transport can focus organic matter. A stationary animal is not necessarily passive if it is positioned where the water works for it. Many deep-sea communities are arranged around flow because flow determines what arrives. Flow can also determine what leaves. Sediment plumes, larvae, contaminants, and dissolved chemicals may move beyond the point where they are produced. This makes impact assessment difficult. A disturbance at one site may not remain neatly inside a boundary drawn on a map. The ocean moves through boundaries. It carries particles across them. It carries genetic material, sound, and chemical signals. Managing pressure worlds therefore requires thinking in 3 dimensions and, over time, not only marking polygons on the seafloor. 3-dimensional thinking is essential in the midwater, where there is no floor, no wall, and no obvious landmark for the camera to hold. Animals' lives suspended in volume. A siphonophore may extend vertically. A fish may migrate hundreds of meters. A predator may attack from below because silhouettes matter. A small crustacean may spend daylight at one depth and night at another. The habitat is not a place to stand, but a depth range, a light field, a pressure range, a prey layer, and a schedule. The pressure world here is architecture without walls. This can make midwater footage feel especially strange. The vehicle moves, but there is no seafloor to prove motion. Particles drift. An animal appears and disappears. Depth is shown only by numbers. Without those numbers, the frame could be anywhere in darkness. But the number changes everything. A transparent animal at 700 meters is not the same ecological fact as a similar animal at 2,000. The pressure, light, food, and predators differ. The depth reading is the missing landscape. In the trenches, the landscape returns with force. Walls descend, sediment ponds, slopes fail, and the bottom receives material from above and from the sides. A trench can act like a funnel, concentrating organic matter more than the open abyss around it. This helps explain why life can persist at depths that seem too extreme if pressure alone is considered. Food supply, though limited, may be enhanced by topography. The deepest places are not simply the farthest from sunlight. They are shaped by the geometry of the seafloor around them. Trench isolation also means evolution can proceed separately in different hadal systems. Species found in one trench may not occur in another. Similar ecological roles may be filled by related but distinct animals. The hadal zone is therefore not one uniform band at the bottom of the ocean. It is a scattered archipelago of deep basins, each with pressure, food, and geography combining in its own way. To call something hadal is to name a depth category, not a complete ecology. The same caution applies to the word abyssal. The abyssal plain under the North Pacific is not identical to the abyssal plain under the South Atlantic. Productivity above, sediment type, oxygen, current, nodule abundance, and distance from land all matter. A sea cucumber community in one basin may differ from another. A sponge using nodules in one region may not occur elsewhere. The deep sea's vastness can hide regional identity. Careful science brings that identity back. Regional identity matters for conservation because one damaged area cannot always be replaced by another that looks similar on a course map. If species composition differs, if larvae do not move freely between regions, if substrate took millions of years to form, then setting aside one area while disturbing another may not preserve the same biological reality. The deep sea challenges simple trade-offs because so much of its diversity is still being mapped. The less we know, the more cautious equivalence should be. A final pressure world exists inside the act of attention itself. Most people will never enter a submersible or stand in a control room during a dive. They will meet the deep sea through footage, narration, museum specimens, maps, and the occasional image of an animal brought up from darkness. That distance can make the ocean feel symbolic, as if it were there to represent mystery or fear. But the animals are not symbols first. They are organisms occupying water, sediment, rock, current, chemistry, and pressure. A good descent of the mind should leave them more real, not more mythical. Realness depends on scale. A single amphipod is small enough to overlook, but at a baitfall, many amphipods can strip tissue with astonishing speed. A single marine snow particle is nearly weightless, but trillions of particles help feed the deep ocean and move carbon downward. A single pressure housing is a technical object, but thousands of such housings have opened the deep to measurement. A single whale fall is local, but across an ocean, whale falls form stepping stones of food and habitat. Scale turns small events into systems. The same scale can make responsibility difficult. People are moved by an image of a fish or a coral, but policy must respond to basins, currents, species ranges, mining claims, fishing grounds, and carbon cycles. The deep sea is too large for affection alone and too specific for abstraction alone. It requires both: the ability to care about a small animal in a beam of light, and the ability to think about the invisible processes that continue far beyond that beam. This is why a script about pressure should not end with pressure as a spectacle. The force is real, and it can be frightening, but it is also measurable and ordinary within the ocean's physics. What matters is how that force organizes possibility. It prevents casual human entry. It demands specialized machines. It shapes cells. It changes gases. It helps keep vent fluids in states that build chimneys. It surrounds animals whose bodies work because they do not carry the wrong kind of emptiness. Pressure is not the whole story, but without it the story would not be the deep sea. There is also comfort in the fact that the deep sea is not waiting to be understood all at once. It can be approached carefully. A map, a dive, a sample, a pressure chamber, a genetic sequence, a return visit. Each step narrows one uncertainty while leaving many others intact. This is how knowledge usually grows when the subject is too large for conquest. Not by declaring the darkness solved, and not by worshiping it as unknowable, but by letting evidence accumulate until the shape of a real world becomes clearer. The metal that would collapse tells us about our limits. The animals that do not collapse tell us about life's range. Between them is the narrow path of exploration, a machine strong enough to carry surface tools downward, gentle enough to observe without destroying, and honest enough to return with data rather than certainty beyond the evidence. That path is narrow, but it has already changed what humans know about Earth. It has shown that the planet's largest habitat is not empty space beneath waves. It is a living ocean under pressure. Not every future descent will reveal a new species or a dramatic scene. Some will show sediment, particles, small animals, and long, quiet intervals. Those dives will still matter because most of the deep sea is made of such intervals. They teach scale, scarcity, patience, and method. They teach that a world does not need to entertain constantly to be significant. The pressure world continues whether the footage is spectacular or plain, and the plain footage may be closer to the truth of its daily life. So the title becomes less a sentence about destruction and more a doorway into comparison. Metal collapses when it enters depth in the wrong form. Life continues when it has been shaped by depth over generations. Human knowledge advances when machines briefly survive long enough to witness that difference. Somewhere below the surface, beyond the last natural light, pressure is still pressing from every side. A housing resists it. A jelly accepts it. A fish belongs to it. And the ocean, indifferent to all three, remains immense, dark, and alive. This is why the deep sea remains worth returning to even when the first shock of pressure has passed. After the numbers are understood, after the engineering is explained, after the idea of metal collapse becomes familiar, the living details remain. The angle of a fin, the slow opening of a muscle, the shape of a track in mud, the way a shrimp holds itself at the edge of a vent flow. These are not decorations around an extreme environment. They are the environment made visible through life. A pressure world is most honestly approached as a habitat first and a hazard second. It is hazardous to us because we are not made for it. It is habitat to the organisms whose bodies, behaviors, and histories fit its demands. That difference should guide every descent, every sample, every story, and every decision made above the water about what may happen below it. In the end, pressure worlds are not defined only by what they do to metal. They are defined by what continues under the pressure. A sea ctenophore beating its comb rows. A rat tail following scent. A tube worm receiving chemical energy through bacteria. A mussel bed at a seep. A sea pig crossing sediment. A snailfish in a trench. A whale bone covered with worms. A pressure housing descending beside them, bright and temporary. The machine and the animal share the same water for a few minutes, but they belong to it in different ways. The machine will return to the ship if everything works. It will be rinsed with fresh water. Its data will be copied. Its samples will be labeled. Its scratches will be inspected. The animals will remain, unless one has been collected, and the pressure will remain around them without becoming an event. The camera beam will be gone. Marine snow will continue falling through the dark. Currents will continue crossing slopes, plains, vents, seeps, and trenches. The ocean will close over the brief path of light. This is what makes the deep sea difficult to hold in the mind. It is both fragile and forceful. It can crush metal and shelter delicate bodies. It can preserve a plastic bottle and dissolve a shell. It can appear empty and contain immense living volume. It can be remote and connected. It can seem timeless and still respond to surface change. Every simple description fails eventually, because the deep ocean is not a single mood. It is a system of pressure worlds, each one real enough to damage our machines and precise enough to sustain life. The next time a depth number glows on a monitor, it may help to think of it not only as distance from the surface, but as entry into another set of rules. At 500 meters, light is fading, and animals are migrating. At 1,000, pressure has already left ordinary human experience behind. At 4,000, the abyssal plain may stretch under near freezing water. At 6,000, the hadal boundary begins. At 11,000, only the most specialized machines and organisms remain. The number is not just a measurement, it is a summary of what must be survived, accepted, or avoided. And somewhere below that number, beyond the narrow reach of the light, an animal is not surviving an impossible place. It is living in its possible place. Its body does not need to imagine the surface. It does not need to know that metal can collapse. It does not need to know that people on a ship are watching a screen and trying to understand. It only needs the pressure to remain what it is, the water to carry what it carries, the darkness to hold its signals, and enough food to arrive before the next long interval of waiting. That is the final correction the deep sea offers. Pressure is not merely a danger, it is a condition. For us, it is a barrier measured in ratings, hull thickness, and risk. For the animals, it is part of the architecture of home. The same force that can fold an empty chamber inward can surround a jelly without drama, hold a vent fluid in a liquid state, press over a whale skeleton feeding worms, and fill a trench where fish move slowly across sediment. The ocean is not gentle. But it is not empty, and it is not only destructive. The RUV rises at the end of the dive. The depth number runs backward. The pressure falls away from the machine, meter by meter. Lights fade in the water above. The surface returns as a shimmer, then as waves, then as air. On deck, people reach for lines and hooks, and the vehicle comes home carrying images of places where most human-made hollows would not survive. Below, the pressure worlds remain closed over, dark and working, filled with animals that do not need rescue from the depth, only the continuation of the conditions that made their lives possible.